Right now, 40.66 light-years from your position in space, something is happening that breaks every rule we created to protect ourselves from cosmic disappointment. A world the size of Earth orbits through darkness under a dim red sun that barely qualifies as a star. The planet completes its year in 6 days. It receives 60% of the starlight you take for granted. Its star erupts 6 times every single day in magnetic tantrums that should have sterilized everything within its gravitational reach 2 billion years ago. Every prediction says this world should be dead. Every model says its atmosphere should have been stripped away when the universe was young. Every calculation performed by every astronomer who first pointed a telescope at this system in 2016 said we would find nothing but bare rock cooked by radiation and frozen by distance. The James Webb Space Telescope looked anyway. And what it found, hiding in the spectrum of filtered starlight, changes absolutely everything we understand about where life can survive in this galaxy. They call it TRAPPIST-1e. The 4th planet in a system that contains 7 Earth-sized worlds packed so tightly together that from the surface of one you could see the others hanging in your sky larger than our moon. A miniature solar system that would fit comfortably inside Mercury's orbit, compressed into a space so small it defies the architecture that built our own cosmic neighborhood. For 3 years, scientists aimed Webb's infrared instruments at this world every time it crossed the face of its volatile star. They measured the light filtering through atmosphere that might not exist. They analyzed chemical signatures masked by stellar tantrums. They built computer models to separate planetary signals from the screaming noise of a star that erupts more frequently than your heart beats. The data came back in September of 2025. 2 papers published in the Astrophysical Journal Letters, hundreds of pages of analysis performed by teams at MIT and the Space Telescope Science Institute, and the University of St. Andrews and a dozen other institutions. All of them searching for one impossible thing: evidence that atmosphere exists 40 light-years from Earth on a world orbiting a star barely hotter than a candle flame. They didn't find proof. What they found is worse. They found hints, tantalizing suggestions that hydrogen and helium aren't dominating the spectrum. Statistical preferences for nitrogen-rich atmosphere with trace methane. Measurements that rule out Venus and Mars scenarios while leaving the door open to something we've never seen before. "We're seeing something tantalizing," said Ryan McDonald at the University of St. Andrews. "If it is confirmed, it is a huge deal. We would have the first atmosphere on a habitable zone rocky planet beyond our own solar system." The word "if" carries the weight of 200 years of astronomical disappointment. The conditional tense holds the accumulated trauma of every false start in the search for worlds like Earth. But the data refuses to cooperate with pessimism. The transmission spectra show signatures that bare rock cannot explain. The wavelength-dependent signals suggest molecular absorption happening somewhere between star and telescope. TRAPPIST-1e might have air. And if one world this hostile can hold atmosphere against radiation that strips planets to their cores, then every assumption we made about where to search for life was catastrophically wrong. The galaxy contains 400 billion stars. 200 billion of them are red dwarfs, like TRAPPIST-1. Small, cold, violent stars that outnumber sun-like stars by a factor of 10. We ignored them. We assumed their flares made them death traps. We built our models for habitability around yellow stars like our Sun, and we dismissed the most common stellar environment in the Milky Way as a cosmic graveyard. The spectrum of TRAPPIST-1e says we were wrong. This is the story of how one planet 40 light-years away shattered the search for life in the universe. This is the account of stellar violence and atmospheric survival, and a technology that lets us taste alien air across distances that would take spacecraft 1 million years to cross. This is the chronicle of what happens when impossible becomes probable, and probable becomes terrifying. Prepare yourselves. We begin. For 50 years, we told ourselves a comforting lie about where to search for life in the galaxy. We built our models around stars like the Sun, yellow dwarfs burning hydrogen at 5,600 degrees Celsius. Stable, predictable, well-behaved stellar citizens that maintain their luminosity for billions of years without throwing cosmic tantrums. We had good reasons. Our entire understanding of habitability was constructed from a sample size of 1. Earth orbits a G-type star at 93 million miles. The distance creates a thermal equilibrium that keeps oceans liquid. The stellar stability provides consistent energy for photosynthesis. The radiation environment remains calm enough that atmosphere persists for 4.5 billion years. This became our template. This became our prison. The problem reveals itself in the mathematics of stellar demographics. G-type stars, like our Sun, represent 7.6% of the stellar population in the Milky Way. They're rare, beautiful, stable, and cosmically irrelevant when you're searching for habitable real estate across a galaxy containing 400 billion stars. M-type red dwarfs represent 75% of all stars. 300 billion of them populate our galaxy alone. They're small, barely 1/10 the mass of the Sun cold, with surface temperatures hovering around 2,500 degrees Celsius. Dim, radiating most of their energy in infrared wavelengths invisible to human eyes. And according to every habitability model constructed before 2015, they're graveyards. The case against red dwarfs was comprehensive. It started with stellar violence. Red dwarf stars are fully convective, meaning their interiors churn like boiling water. Energy moves through the entire stellar mass via convection rather than radiative transport. This creates magnetic fields of extraordinary complexity and power. The magnetic fields twist, they snap. They reconnect in events that release more energy in minutes than our Sun produces in months. These are stellar flares, and red dwarfs produce them with terrifying frequency. TRAPPIST-1e, the star at the center of our story, erupts approximately 6 times per day. That's 42 flares every week. 2,184 flares annually. Over the star's 7.6 billion year lifetime, it has produced roughly 16 trillion flares. Each flare releases a broadband spectrum of radiation. Visible light, ultraviolet, X-rays, high-energy particles accelerated to relativistic speeds by magnetic reconnection events. The radiation environment around a flaring red dwarf makes solar flares look gentle by comparison. What does this radiation do to planets? It strips atmosphere. The mechanism is brutal and efficient. High-energy photons slam into atmospheric molecules, breaking chemical bonds. Ultraviolet radiation dissociates water into hydrogen and oxygen. The hydrogen, being light, achieves escape velocity and bleeds into space. X-rays ionize the upper atmosphere, creating charged particles that get swept away by stellar wind. A planet orbiting a red dwarf doesn't lose its atmosphere gradually over billions of years. It loses atmosphere catastrophically during each flare event. Multiply this by 16 trillion flares, and you're left with bare rock. The radiation problem compounds with orbital mechanics. Red dwarfs are dim, producing only 0.055% of the Sun's luminosity in the case of TRAPPIST-1e. For a planet to receive enough energy to maintain liquid water, it must orbit very close to its star. TRAPPIST-1e orbits at 0.029 astronomical units. That's 2.9% of Earth's distance from the Sun. The planet sits closer to its star than any planet in our solar system sits to our Sun. Mercury orbits at 0.38 astronomical units. TRAPPIST-1e is 13 times closer to its star than Mercury is to ours. This proximity creates tidal locking, the same gravitational forces that locked the Moon's rotation to Earth lock planetary rotation to red dwarf stars. One hemisphere faces eternal day, the other faces eternal night. The temperature differential should be catastrophic. Computer models predicted this scenario with depressing consistency. The day side heats beyond the boiling point of water. The night side freezes below the condensation point of carbon dioxide. Any atmosphere thick enough to transport heat between hemispheres gets destroyed by stellar flares. Any atmosphere thin enough to survive radiation can't move enough thermal energy to prevent collapse. The models showed planets around red dwarfs becoming cosmic titans, with one side baking under dim red light while the other side freezes into darkness. Except Titan has atmosphere because it orbits Saturn, not a flaring red dwarf. These planets had nothing. Bare rock heated on one side and frozen on the other with no atmosphere to moderate the extremes. And then there was the life problem. Even if somehow atmosphere survived, even if liquid water persisted in some narrow habitable band between eternal day and eternal night, photosynthesis would fail. Red dwarfs radiate primarily in infrared wavelengths. Plants evolved to harvest visible light from a yellow star. The photosynthetic machinery that powers Earth's biosphere might not function under a red sun. Multiple studies calculated the photosynthetic potential of planets orbiting TRAPPIST-1. The conclusions were grim. Radiation flux in wavelengths suitable for photosynthesis came out to approximately 1/10 what Earth receives. Plants would starve for light. Ecosystems would collapse before they began. The case was closed. Red dwarfs were death traps. Their planets were corpses. The search for habitable worlds should focus on the 7.6% of stars that resembled our Sun. This conclusion had consequences. NASA's Kepler mission, launched in 2009 to find Earth-sized planets in habitable zones, prioritized Sun-like stars in its target selection. The Transiting Exoplanet Survey satellite, launched in 2018, expanded the search but still favored brighter stars for easier follow-up observations. The astronomical community reached consensus. If you wanted to find another Earth, you searched around another sun. Red dwarfs were a distraction, a statistical waste of observing time. But consensus in science is just collective opinion that hasn't met contradictory data yet. The first cracks appeared in 2016 when the TRAPPIST-1e telescope in Chile detected 3 transiting planets around an ultra-cool red dwarf barely 40 light-years from Earth. The discovery was interesting but not revolutionary. 3 rocky planets orbiting a violent star. Probably airless, almost certainly dead. Then, in February 2017, additional analysis revealed 4 more planets, 7 Earth-sized worlds orbiting a single red dwarf star. The system was compact, fitting inside Mercury's orbit. 3 planets sat in the theoretical habitable zone, where temperatures might allow liquid water if atmosphere existed. The discovery changed the conversation. Not because anyone thought TRAPPIST-1 planets were habitable. They didn't. The star's flaring activity made that impossible. But the system provided something unprecedented: a laboratory. 7 planets, all roughly Earth-sized, all transiting their star from our line of sight, all orbiting so close that transits happen frequently. TRAPPIST-1b completes an orbit every 1.5 days. TRAPPIST-1e finishes its year in 6.1 days. You could observe multiple transits of multiple planets in a single week. This made atmospheric characterization theoretically possible. When a planet transits its star, starlight filters through its atmosphere if one exists. Different molecules absorb different wavelengths, leaving spectral fingerprints. By measuring these fingerprints, astronomers can determine atmospheric composition from 40 light-years away. The technique is called transmission spectroscopy, and it revolutionized exoplanet science in the early 2000s. But it requires specific conditions. The planet must transit its star from our viewing angle. The star must be bright enough that we can detect subtle changes in its light spectrum. The planet's atmosphere must be thick enough to produce measurable signals. TRAPPIST-1 met these requirements, not because the planets were likely to have atmospheres, but because the system's geometry was perfect and the star's proximity made detailed observations possible. So astronomers observed. The Hubble Space Telescope pointed its instruments at TRAPPIST-1. Spitzer Space Telescope devoted 500 hours to studying the system. Ground-based observatories tracked transits across multiple wavelengths. The results were discouraging but expected. No clear atmospheric signatures emerged. The planets appeared to be exactly what models predicted: bare rock, stripped clean by stellar radiation. TRAPPIST-1b, the innermost planet orbiting closest to the star, showed no evidence of atmosphere. TRAPPIST-1c showed flat transmission spectra consistent with an airless world. The red dwarf graveyard hypothesis held. These planets were dead. The hundreds of billions of worlds orbiting M-type stars throughout the galaxy were probably dead too. Earth was special not just because it had life, but because it orbited a rare, stable star. This was the status of knowledge in July 2022 when the James Webb Space Telescope activated its instruments and prepared to look deeper into the TRAPPIST-1 system than any observatory before it. What Webb would find wasn't evidence that the models were completely wrong. It was evidence that the models were incomplete. That stellar violence and atmospheric survival could coexist in ways we never predicted. That the red dwarf graveyard might contain a few survivors hiding in spectral signatures too subtle for Hubble to detect. The graveyard was about to give up a ghost. The James Webb Space Telescope is not designed to be user-friendly. It sits 1 million miles from Earth at the second Lagrange point, a gravitationally stable location where the combined pull of Earth and Sun keep the telescope in permanent alignment. This distance places Webb 4 times farther from Earth than the Moon. You cannot service it. When the Hubble Space Telescope's instruments failed, astronauts flew up in the space shuttle and installed replacements. When Webb's instruments fail, they fail permanently. The telescope becomes a $6.5 billion piece of orbital debris. You cannot point it at just anything. Webb's massive sunshield must always face the Sun to keep the telescope's instruments cooled to -233 degrees Celsius. This constraint means roughly 40% of the sky is inaccessible at any given time. Targets must be carefully scheduled months in advance. And you definitely cannot get much time on it. Every astronomer on Earth wants Webb observations. For Cycle 4 of the telescope's mission, scientists requested 78,000 hours of observing time. Only 8,700 hours were available. Your proposal competes against 9 others. 8 get rejected. So when the JWST telescope scientist team's DREAMS collaboration, deep reconnaissance of exoplanet atmospheres using multi-instrument spectroscopy, received approval to observe TRAPPIST-1e, they knew they held something precious. 4 guaranteed transits, approximately 16 hours of total observing time spread across mid to late 2023. 4 chances to catch starlight filtering through atmosphere that might not exist. The weapon they wielded was NIR-SPEC, the near-infrared spectrograph, arguably the most sophisticated instrument ever launched into space for exoplanet characterization. Understanding why NIR-SPEC matters requires understanding what makes atmospheric detection so impossibly difficult. Start with the signal. When TRAPPIST-1e transits its star, it blocks 0.724% of the star's light. That's the total transit depth, the amount by which the star dims when the planet crosses in front of it, 0.724%. 7,240 parts per million. Now consider atmosphere. If TRAPPIST-1e has an Earth-like atmosphere, that atmosphere extends perhaps 60 kilometers above the planet's surface. During transit, starlight doesn't just pass by the planet. It grazes through this thin shell of gas at the planet's limb. The atmospheric signal, the additional blocking caused by atmosphere absorbing light at specific wavelengths, measures approximately 20 to 50 parts per million. 20 parts per million on top of 7,240 parts per million. You're looking for a signal that's 0.3% the size of the total transit depth. It gets worse. The star itself varies in brightness. TRAPPIST-1 erupts and flares 6 times per day. Between flares, the star's surface writhes with magnetic activity. Star spots, cooler regions similar to sunspots, but covering much larger fractions of the stellar surface, rotate in and out of view. Faculae, hotter magnetic regions, appear and disappear unpredictably. These stellar variations create brightness changes of hundreds to thousands of parts per million. The thing you're trying to measure, the atmospheric signature, is 10 to 50 times smaller than the noise created by the star itself. This is why Hubble failed to detect atmospheres around TRAPPIST-1 planets. Hubble's instruments were not sensitive enough in the infrared wavelengths where red dwarf stars emit most of their energy. Hubble worked in optical and near ultraviolet, wavelengths where TRAPPIST-1 barely glows. The signal-to-noise ratio made atmospheric detection impossible. Webb operates differently. NIR-SPEC covers wavelengths from 0.6 to 5.3 microns, deep in the infrared. This range includes the peak emission of TRAPPIST-1's spectrum. More infrared photons mean better signal. Better signal means you can detect smaller atmospheric features. The instrument uses a microshutter array, a grid of 62,000 individually controllable shutters, each measuring 0.2 by 0.4 arc-seconds. During an observation, flight software opens only the shutters aligned with your target while keeping the rest closed. This blocks contaminating light from other sources and maximizes the purity of your spectrum. Light entering through the open shutters hits a collimator that straightens the light rays into parallel beams. The beams pass through one of 6 optical elements, prisms, or gratings that split light into its component wavelengths. The separated wavelengths hit a detector array cooled to 39 Kelvin, -234 degrees Celsius, cold enough that thermal noise becomes negligible. The detector measures light intensity at 2,948 different wavelengths simultaneously. This is a spectrum. The shape of this spectrum, which wavelengths are bright and which are dim, tells you what molecules are absorbing light in the planet's atmosphere. Except you're not measuring the planet's spectrum. You're measuring the combined spectrum of star plus planet during transit, compared to the spectrum of the star alone before or after transit. The difference between these two measurements divided by the star alone spectrum gives you the transmission spectrum of the planet. This transmission spectrum shows how the planet's apparent size changes with wavelength. If the planet has no atmosphere, its size is the same at all wavelengths. The transmission spectrum is flat. If the planet has atmosphere containing molecules that absorb specific wavelengths, the planet appears larger at those wavelengths because the atmosphere is blocking additional light. The transmission spectrum shows peaks and valleys corresponding to molecular absorption. Water vapor absorbs strongly at 1.4 and 1.9 microns. Carbon dioxide has distinctive absorption bands at 2.7 and 4.3 microns. Methane absorbs at 2.3 and 3.3 microns. By measuring the transmission spectrum, you can determine which molecules are present and in what quantities. Theory makes it sound simple. Reality is considerably more hostile. The DREAMS team planned their observations with obsessive care. Nestor Espinosa at the Space Telescope Science Institute led the NIR spec observations. Anna Glidden at MIT handled atmospheric retrieval, the process of determining which atmospheric compositions best match the observed spectrum. Ryan McDonald at the University of St. Andrews developed models for stellar contamination. They chose the PRISM mode for NIR spec, which provides low spectral resolution but high sensitivity across the full wavelength range. Low resolution means you can't distinguish between closely spaced absorption features, but high sensitivity means you can detect faint signals. For a target as dim as TRAPPIST-1e, sensitivity was more important than resolution. Each transit observation required approximately 4 hours. The observation sequence went like this. Start observing before the transit begins to establish the baseline stellar spectrum. Continue observing as the planet crosses in front of the star, taking spectra throughout the transit. Keep observing after the planet finishes its transit to re-establish the baseline. The timing had to be perfect. TRAPPIST-1e's orbit was known to extraordinary precision from years of ground-based monitoring and Spitzer observations. The planet transits its star every 6.0992 days. Each transit lasts 53.8 minutes from first contact, when the planet's edge touches the star's edge, to fourth contact, when the planet completely clears the stellar disk. If Webb started observing too late, it would miss the crucial ingress phase when the planet is partially blocking the star. If it observed during a stellar flare, the flare's radiation would swamp the atmospheric signal. If cosmic rays hit the detector during critical moments, the contamination would ruin the spectrum. The first observation happened in June 2023, the second in August, the third and fourth in late 2023. 4 transits. 4 independent measurements of the same planet's atmosphere. 4 chances to detect molecules hiding in starlight. The data came down from Webb as photon counts at 2,948 wavelengths measured every 0.7 seconds throughout each 4-hour observation window. Raw numbers. Millions of them. The detector recorded approximately 20 million photons per second from TRAPPIST-1 during transit. But these photons carried systematic errors. Cosmic rays struck the detector about once every 3 seconds, creating false signals that had to be identified and removed. The detector's sensitivity varied slightly across its surface, requiring flat field corrections. The telescope's pointing drifted by tiny amounts, causing the star's light to fall on slightly different pixels and requiring drift corrections. The data reduction pipeline handled these corrections automatically, but careful checking was essential. A single uncorrected cosmic ray hit at the wrong moment could create a false absorption feature that looks exactly like a molecular signature. A drift correction applied incorrectly could erase a real atmospheric signal. After data reduction, the team had 4 transmission spectra of TRAPPIST-1e, 4 measurements of how the planet's apparent radius changes with wavelength from 0.6 to 5.3 microns. The spectra did not match each other. Each of the 4 observations showed different features. The first spectrum showed a possible absorption feature near 2.3 microns. The second spectrum showed different features at 3 microns. The third and fourth spectra disagreed with the first 2 and with each other. This disagreement between observations of the same planet during different transits, was the signature of stellar contamination. The star itself was changing between observations, creating different spectral features that mimicked or masked planetary atmospheric signatures. TRAPPIST-1's surface was not uniform. Star spots covered perhaps 5 to 10% of the visible hemisphere at any given time. These spots rotated into and out of view as the star spun on its axis with a rotation period of approximately 3.3 days. When TRAPPIST-1e transited across a star spot during one observation, but not during another, the resulting spectra looked different, even though the planet's atmosphere hadn't changed. Faculae created similar problems. These bright magnetic regions had different spectra than the surrounding photosphere. A transit crossing a facula produced different apparent atmospheric features than a transit crossing quiet stellar surface. And then there were flares, unpredictable, unavoidable. The DREAMS team actually observed a flare during one of their transits. The star's brightness suddenly increased by 0.003% for 11 minutes during the observation window. This flare was small by TRAPPIST-1 standards, barely worth noticing compared to the massive eruptions the star regularly produces, but it was large enough to distort the transmission spectrum. The 4 spectra lay on the table like a crime scene. The evidence pointed in contradictory directions. Something was creating absorption features at various wavelengths. But was it the planet's atmosphere, or the star's surface, or some combination of both? This ambiguity is what made TRAPPIST-1e's atmosphere so difficult to confirm. The planetary signal existed somewhere in these spectra, but it was buried beneath stellar noise of comparable amplitude. Extracting truth from this data required techniques that pushed the boundaries of astronomical analysis. The team turned to Gaussian process regression, a statistical method for modeling complex correlations in data. The idea is to let the data tell you what the stellar contamination looks like, rather than assuming a specific model. The Gaussian process learns the pattern of stellar variability from the observations themselves, then subtracts that learned pattern to reveal the underlying planetary signal. It's a powerful technique, but it's also dangerous. If you're not careful, the Gaussian process can subtract away real planetary features while modeling them as stellar noise. Or it can leave behind stellar artifacts while interpreting them as planetary atmosphere. The method requires careful validation and cross-checking. Anna Glidden spent months developing and testing atmospheric retrieval models that could handle stellar contamination. Ryan McDonald built parallel models using different statistical approaches. The 2 teams worked independently, each analyzing the same data with different methods to see if they reached the same conclusions. If both methods agreed, you could trust the result. If they disagreed, you had more work to do. The weapon had been fired, 4 transits observed, millions of photons counted, sophisticated analysis techniques deployed. Now came the moment of truth. What did the spectrum of TRAPPIST-1e actually reveal about its atmosphere? The answer would reshape the search for habitable worlds across 300 billion red dwarf stars. The transmission spectrum of TRAPPIST-1e does not look like Earth. It does not look like Venus or Mars or Titan or any world in our solar system. It looks like statistical noise, with hints of pattern hiding underneath stellar chaos. Anna Glidden saw it first, in the preliminary data from the first transit observation. A flat baseline with scatter, exactly what you'd expect from instrumental noise and stellar variability. But embedded in that scatter were subtle correlations, wavelength regions where the scatter wasn't random but showed weak systematic trends. She ran the data through her atmospheric retrieval code, a sophisticated Bayesian framework that compares observed spectra to millions of theoretical models. The code generates random atmospheric compositions, calculates what their transmission spectra should look like, then asks how well each model matches the observations. Models that match poorly get discarded. Models that match well get refined and tested further. The retrieval ran for 72 hours on a computing cluster at MIT, testing scenarios ranging from hydrogen-dominated atmospheres like Jupiter's to exotic chemistries never seen in our solar system. Each scenario produced a probability score, a number indicating how well it matched the Webb observations. The results came back in probability distributions rather than definitive answers. Science at this precision doesn't give you certainty. It gives you likelihood ratios and confidence intervals and probability densities that you have to interpret carefully. The first clear result was negative. Hydrogen-rich atmospheres showed probabilities below 3%. This was significant. If TRAPPIST-1e had retained a primordial atmosphere from its formation, that atmosphere would be dominated by hydrogen and helium, the most abundant elements in the universe. Such atmospheres are puffy, extending far above the planet's surface because hydrogen is light. The transmission spectrum should show this. A hydrogen atmosphere creates large transit depth variations across wavelengths because the extended atmosphere blocks different amounts of light at different colors. The signal should be obvious, hundreds of parts per million in amplitude. Webb saw nothing like this. The spectrum was too flat. The variations too small. Whatever atmosphere TRAPPIST-1e might have, it wasn't primordial hydrogen. This absence tells a violent story. When TRAPPIST-1e formed 4.6 billion years ago in the protoplanetary disk surrounding the young red dwarf, it should have accreted hydrogen and helium along with rock and metal. That primordial envelope should still be there. Its absence means it was destroyed. The leading suspect is stellar radiation. During its first 100 million years, TRAPPIST-1 would have been even more active than it is now. Young red dwarfs are violent, their magnetic fields stronger, and their flares more frequent as they contract toward the main sequence. The radiation flux at TRAPPIST-1e's orbital distance during this epoch was catastrophic. Extreme ultraviolet photons, wavelengths short enough to ionize atoms with single impacts, would have flooded the planet's upper atmosphere at intensities 10,000 times higher than Earth experiences. X-ray radiation, capable of heating atmospheric gas to millions of degrees, bombarded the dayside continuously. This radiation drives atmospheric escape through a process called photoevaporation. High-energy photons hit atmospheric molecules, breaking them into atoms and ions. The energy absorbed heats the atmosphere until it reaches temperatures where gas achieves escape velocity. Hydrogen, being the lightest element, escapes most easily. Over millions of years, the entire primordial envelope boils away into space. Computer models of this process are brutal. Simulations show planets at TRAPPIST-1e's orbital distance losing primordial atmospheres completely within 10 to 100 million years. The hydrogen is gone. The helium is gone. Anything volatile enough to have existed in gas form during the planet's youth has been stripped away by stellar fury. So if TRAPPIST-1e has atmosphere now, 4.6 billion years after formation, that atmosphere is secondary. It came later. It formed from gases released from the planet's interior, through volcanic activity, through comet impacts, through processes that continued long after the primordial envelope disappeared. This possibility changes everything about what you're looking for in the spectrum. Secondary atmospheres on rocky planets tend to be dominated by heavier molecules. On Earth, nitrogen makes up 78% of atmospheric mass. Carbon dioxide, water vapor, argon, and trace gases make up the rest. On Venus, Carbon dioxide dominates at 96%, with nitrogen as a distant second. On Mars, the thin atmosphere is 95% carbon dioxide. These molecules produce different spectral signatures than hydrogen. Carbon dioxide has strong absorption bands at 2.7 microns and 4.3 microns. Water vapor absorbs at 1.4 and 1.9 microns. Methane, if present, creates features at 3.3 microns. Nitrogen is transparent across most infrared wavelengths, essentially invisible to transmission spectroscopy. Anna Gliddon's retrieval code tested all these scenarios against the 4 transit observations. Venus-like atmosphere with 90 bar surface pressure. Mars-like atmosphere with 0.006 bar pressure. Earth-like with 1 bar pressure and 78% nitrogen. Exotic compositions with methane or sulfur compounds or ammonia. The code ranked each scenario by its Bayesian evidence, a statistical measure that accounts for both how well the model fits the data and how complex the model is. Simple models that fit poorly score low. Complex models that fit well but require many parameters also score low because they might be overfitting noise. The ideal model fits the data with minimal complexity. The Venus scenario scored poorly. A thick carbon dioxide atmosphere with 90 bar surface pressure would create obvious absorption features at 2.7 and 4.3 microns. The Webb spectrum showed nothing this strong. The evidence against Venus-like atmosphere exceeded 3 sigma, meaning less than 0.3% probability. The Mars scenario also scored poorly. A thin carbon dioxide atmosphere would show smaller absorption features than Venus, but they should still be detectable with Webb's sensitivity. Again, the spectrum was too flat. The evidence against Mars-like atmosphere was approximately 2 sigma, meaning less than 5% probability. This negative evidence from September 2025 generated headlines. MIT News published a story titled "Study Finds Exoplanet TRAPPIST-1e is Unlikely to Have a Venus or Mars-like Atmosphere." Scientific American ran an article emphasizing how these findings narrowed the possibilities. The astronomy community recognized this as progress, even though it was negative progress. You learn something when you rule out scenarios. You learn that TRAPPIST-1e, if it has atmosphere, has something we haven't seen before in our solar system. Something neither thick like Venus nor thin like Mars. Something that requires different chemistry or different surface conditions or different evolutionary pathways. But the retrieval code didn't just produce negative results. It also identified 2 scenarios that remained statistically viable. 2 possibilities that the Webb data couldn't distinguish between. The first scenario. TRAPPIST-1e is a bare rock with no atmosphere at all. The transmission spectrum is flat because there's nothing to absorb starlight at the planet's limb. The small variations Webb detected are purely stellar contamination, artifacts of star spots and faculae rotating across the stellar surface. This scenario had probability around 40 to 45%, depending on how you modeled stellar activity. The second scenario, TRAPPIST-1e has a nitrogen-dominated atmosphere with trace amounts of heavier molecules. Nitrogen is transparent in the infrared, so it doesn't create obvious absorption features. But trace constituents like methane or carbon dioxide, present at concentrations below 1%, could create subtle features hiding in the noise. This scenario also had probability around 40 to 45%. These 2 scenarios are fundamentally different, but produce nearly identical spectra. A bare rock looks flat because nothing is there. A nitrogen atmosphere looks flat because nitrogen is invisible. You need additional observations to break the degeneracy. But here's where the analysis got interesting. When Anna Gliddon looked closely at the nitrogen scenario, examining which specific compositions best matched the Webb data, she found a tentative preference. The models slightly favored scenarios including methane at trace concentrations. The word tentative is critical. This wasn't a detection, it was a hint, a statistical lean in the probability distribution. When you average across all 4 transits and account for stellar contamination using Gaussian process regression, the data shows a weak preference for methane absorption near 3.3 microns. The significance was approximately 2 sigma. In particle physics, you need 5 sigma to claim a discovery. In exoplanet science, the standards are similar. 2 sigma means interesting but not conclusive. It means worth following up with more observations. It means we're seeing something, but we can't be sure it's real. Ryan McDonald's independent analysis using different statistical methods reached the same conclusion. His code also found the tentative methane preference at approximately 2 sigma significance. The agreement between independent teams using different approaches strengthened confidence that the signal might be real rather than an artifact of one particular analysis method. Methane on TRAPPIST-1e would be extraordinary. On Earth, most atmospheric methane comes from biological sources. Methanogenic bacteria in wetlands, in the guts of animals, in rice paddies, produce methane as a metabolic waste product. Geological methane exists, but in much smaller quantities. On a planet orbiting a red dwarf, methane's presence would require explanation. It can't be primordial because stellar radiation destroys light molecules. It must be continuously replenished because ultraviolet light breaks down methane on timescales of thousands of years. So something on TRAPPIST-1e must be producing methane faster than radiation destroys it. 3 possibilities emerged from the analysis. First, volcanic outgassing. If TRAPPIST-1e has an active interior, volcanic eruptions could release methane from the mantle into the atmosphere. This is geological methane, created by chemical reactions in the planet's interior rather than by life. Second, comet impacts. If the TRAPPIST-1 system contains comets that occasionally strike the planets, these impacts could deliver methane and other volatiles to the atmosphere. The methane would be transient, destroyed by radiation over thousands of years, but regular impacts could maintain trace concentrations. Third, biological production. Methanogenic microorganisms could exist in TRAPPIST-1e's environment, producing methane as they metabolize. This would be life, operating under a red sun 40 light-years from Earth, proving that biology can emerge in environments we dismissed as sterile. The data couldn't distinguish between these possibilities. The tentative methane signal, if real, required a source, but provided no information about what that source might be. You'd need many more observations to constrain the methane concentration accurately enough to determine its origin. What the spectrum definitively showed was absence. No thick primordial hydrogen. No Venus-like carbon dioxide greenhouse. No Mars-like thin atmosphere. These were gone, stripped away, or never existed in the first place. What the spectrum tentatively suggested was presence. Possibly nitrogen. Possibly trace methane. Possibly an atmosphere entirely unlike anything in our solar system, constructed from processes and chemistries unique to planets orbiting violent red dwarf stars. The spectrum's secret was ambiguity. Not the frustrating ambiguity of bad data, but the tantalizing ambiguity of a puzzle that needs more pieces. The 4 transit observations provided enough information to eliminate impossible scenarios and identify plausible ones. They didn't provide enough information to reach definitive conclusions. Science has a word for this situation: promising. The DREAMS collaboration published their results in 2 papers in the Astrophysical Journal Letters in September 2025. The first paper, led by Nestor Espinosa, presented the transmission spectra and discussed stellar contamination. The second paper, led by Anna Glidden, presented the atmospheric retrieval results and outlined the remaining viable scenarios. The papers were careful. They emphasized uncertainties. They acknowledged limitations. They presented probability distributions rather than confident claims. This is how science works at the frontier, where every word must be calibrated to match the strength of evidence. But between the carefully calibrated words, the message was clear. TRAPPIST-1e might have atmosphere. And if it does, we're about to discover what air looks like on a world that should be dead. At 10:42 a.m. Greenwich Mean Time on March 19, 2023, TRAPPIST-1 erupted in a flare that released more energy in 11 minutes than our Sun produces in 3 hours. The flare began as a magnetic reconnection event in the star's convective zone, accelerating electrons to relativistic speeds and hurling them through the stellar atmosphere. When those electrons slammed into the photosphere, they heated plasma to temperatures exceeding 10 million degrees Celsius. The superheated material radiated across the electromagnetic spectrum. Visible light, infrared, ultraviolet, X-rays with energies capable of ionizing atoms through single photon impacts. The James Webb Space Telescope was observing TRAPPIST-1e at that exact moment, measuring the subtle dimming as the planet crossed the star's face. The flare appeared in the data as a sudden brightness spike lasting 670 seconds. During those 11 minutes, stellar flux increased by 0.003%, contaminating the transmission spectrum with a signal 30 times stronger than any atmospheric feature the team hoped to detect. This was not an unusual event. This was Tuesday afternoon for TRAPPIST-1. Understanding why TRAPPIST-1e's potential atmosphere matters requires understanding the radiation environment trying to destroy it. Red dwarf stars don't just flare occasionally. They exist in a state of perpetual magnetic violence that makes our sun look serene by comparison. The violence originates in stellar structure. Our sun has two zones. The radiative zone, where energy moves outward through photon diffusion, and the convective zone, an outer layer where hot plasma rises and cool plasma sinks in massive convection cells. These zones are separated by the tachocline, a boundary region where differential rotation creates the magnetic fields that drive solar activity. Red dwarfs like TRAPPIST-1 have no radiative zone. They're fully convective from core to surface. Energy generated by nuclear fusion in the core doesn't diffuse outward through photon collisions. It gets carried by convection currents that churn the entire stellar mass like boiling water. This creates magnetic fields of extraordinary complexity. On the Sun, magnetic field lines emerge from the photosphere in organized loops connecting regions of opposite polarity. These loops store energy that gets released during solar flares. But the Sun's magnetic architecture is relatively simple because the tachocline organizes field geometry. TRAPPIST-1 has no such organization. Convection churns magnetic field lines throughout the stellar volume, twisting and braiding them into configurations so complex that current computer models cannot predict their evolution accurately. The star's surface becomes a writhing mass of magnetic structures that constantly reconfigure themselves. When field lines with opposite polarity get pushed together, they reconnect. The topology changes. Stored magnetic energy converts to kinetic energy in microseconds. Electrons accelerate. Plasma heats. Radiation floods outward. This happens 6 times per day on average. Some flares are small, barely detectable. Others are catastrophic, releasing 10 to the 32 ergs of energy in minutes. That's 1,000 trillion joules. That's the kinetic energy of the asteroid that killed the dinosaurs, released as radiation in the time it takes you to eat lunch. The Kepler K2 mission observed TRAPPIST-1 continuously for 80 days in 2016, monitoring stellar brightness with cadence of 30 minutes. During those 80 days, the mission detected 42 distinct flare events. Statistical analysis suggested this was a lower limit because smaller flares fell below detection threshold. Ward Howard, at the University of Colorado Boulder, led recent analysis of TRAPPIST-1 flares using James Webb observations. His team studied 6 flares captured during exoplanet transit observations in 2022 and 2023, analyzing their spectral evolution with unprecedented detail. The flares show characteristic signatures. They begin with emission in the infrared as accelerated electrons interact with the stellar atmosphere. This infrared emission peaks within seconds to minutes. Then comes optical emission as heated plasma begins to glow. Finally, ultraviolet and X-ray emission as the hottest plasma reaches temperatures where high-energy photons dominate. The spectrum tells you about flare physics. By measuring how much energy comes out at different wavelengths, you can reconstruct what's happening in the stellar atmosphere. The electron beam energy, the plasma temperature, the magnetic field strength, the flare volume. Howard's team used sophisticated models called RADYN, radiation dynamics, to simulate the physics. The models start with magnetic reconnection, calculate electron acceleration, follow those electrons as they slam into the atmosphere, compute the resulting plasma heating, and predict the emerging radiation spectrum. The models matched Webb observations with disturbing accuracy. The flares on TRAPPIST-1 are driven by electron beams carrying approximately 10 to the 28 ergs per second. The beams heat plasma to temperatures between 8,000 and 20,000 Kelvin in the lower atmosphere and up to 10 million Kelvin in the upper atmosphere. This temperature structure matters because it determines what radiation the flare produces. Hot plasma radiates at wavelengths that can destroy atmospheric chemistry on nearby planets. Ultraviolet radiation at wavelengths below 200 nanometers dissociates water molecules. One photon hits H2O, the molecule breaks into hydrogen and hydroxyl radicals. The hydrogen is light enough to escape to space. The oxygen left behind reacts with other atmospheric constituents or gets locked into surface minerals. Over millions of years, planets lose their water. Extreme ultraviolet radiation at wavelengths below 100 nanometers ionizes nitrogen and oxygen. The ions get swept away by stellar wind, charged particles flowing continuously from the star's upper atmosphere. TRAPPIST-1 loses approximately 3 × 10 to the -14 solar masses per year to stellar wind. That doesn't sound like much until you calculate how much atmospheric mass gets stripped from a planet over billions of years. X-rays with energies above 1 kiloelectronvolt penetrate deep into planetary atmospheres, ionizing molecules and heating the upper atmosphere to temperatures where escape becomes possible. The combination of heating and ionization drives hydrodynamic escape, where the entire upper atmosphere expands and flows away into space like water boiling off a hot surface. Computer models of atmospheric escape around TRAPPIST-1 are catastrophic. Simulations by Cecilia Garafo at Harvard-Smithsonian Center for Astrophysics showed that planets at TRAPPIST-1e's orbital distance should lose atmospheres equivalent to Earth's entire atmospheric mass within 10 to 100 million years. The escape rate depends on atmospheric composition. Hydrogen escapes fastest because it's lightest. Helium escapes almost as easily. Heavier molecules like nitrogen, oxygen, and carbon dioxide escape more slowly but still escape given enough time and enough radiation. The models included stellar wind effects. TRAPPIST-1's wind isn't particularly strong compared to active young stars, but at 0.029 astronomical units orbital distance, the wind pressure on TRAPPIST-1e is approximately 50 times what Earth experiences from solar wind. This pressure compresses the planet's magnetosphere if one exists, and creates preferential pathways for atmospheric escape through the magnetic poles. Every simulation showed the same outcome. Primordial atmospheres don't survive. Light volatiles escape within tens of millions of years. Even secondary atmospheres struggle to persist unless volcanic outgassing or other processes replenish atmospheric mass faster than radiation strips it away. This creates a habitability paradox. For liquid water to exist on TRAPPIST-1e's surface, the planet needs atmosphere. Atmosphere provides greenhouse warming to raise surface temperature above freezing. Atmosphere creates pressure to keep water liquid rather than immediately boiling or sublimating. But the radiation environment destroys atmosphere. The closer a planet orbits to receive enough energy for habitability, the stronger the radiation flux that strips atmosphere away. You need to be close to stay warm. Being close means getting irradiated. Getting irradiated means losing atmosphere. Losing atmosphere means losing habitability. The paradox seemed insurmountable until scientists started considering what happens on longer timescales. Atmospheric evolution isn't a one-way process. Yes, radiation strips atmosphere away, but volcanic activity replenishes it. Comet impacts deliver volatiles. Chemical reactions in the crust release gases. The question isn't whether atmosphere gets destroyed. The question is whether destruction and replenishment can reach equilibrium. On Earth, volcanic outgassing has maintained atmospheric pressure for billions of years despite atmospheric escape to space. The rates are balanced. Escape removes approximately 3 kilograms of atmospheric mass per second. Volcanic activity and other processes replenish approximately the same amount. Equilibrium. Could TRAPPIST-1e achieve similar equilibrium? The answer depends on the planet's interior. If TRAPPIST-1e has a molten core driving active geology, volcanic outgassing could replenish atmosphere at rates matching or exceeding escape. The equilibrium atmosphere would be thinner than Earth's, yes, but potentially thick enough to maintain surface pressure and greenhouse warming. Tidal heating strengthens this possibility. TRAPPIST-1e orbits in near resonance with its neighboring planets. TRAPPIST-1e completes 2 orbits for every 3 orbits of TRAPPIST-1d. This orbital resonance creates periodic variations in tidal forces that flex the planet's interior, generating heat through friction. Calculations by Amy Barr at the Planetary Science Institute suggested that tidal heating could maintain volcanic activity on TRAPPIST-1e for billions of years. The heat flow from tidal dissipation might equal or exceed heat flow from radioactive decay in the planet's interior. This drives mantle convection, plate tectonics if the planet has them, and volcanic outgassing sufficient to maintain atmosphere against radiation losses. But there's another complication. The flares don't just strip atmosphere through direct radiation. They also affect atmospheric chemistry in ways that could make the surface uninhabitable even if atmosphere persists. Each flare floods the planet's day side with ultraviolet radiation. This UV breaks apart molecules in the upper atmosphere, creating highly reactive radicals. On Earth, oxygen radicals created by UV radiation form the ozone layer that protects the surface from further UV exposure. On a planet with different atmospheric composition, the radicals might create something else entirely. Computer models by Sukrit Ranjan at the University of Arizona explored photochemistry on TRAPPIST-1e under different atmospheric scenarios. The models started with assumed atmospheric compositions, then calculated how flare radiation would alter those compositions over time. For nitrogen-dominated atmospheres with trace methane, the models predicted accumulation of organic hazes. UV radiation breaks methane into radicals that combine to form more complex organic molecules. These molecules polymerize into particles that create a high-altitude haze layer, similar to what we see on Titan. The haze has 2 effects. First, it shields the surface from UV radiation, potentially making the environment more habitable. Second, it creates anti-greenhouse cooling by reflecting starlight back to space before it reaches the surface. Whether the net effect enhances or reduces habitability depends on haze optical properties and atmospheric composition. For atmospheres with significant carbon dioxide and water vapor, the models predicted buildup of toxic gases like carbon monoxide. UV radiation dissociates carbon dioxide into carbon monoxide and atomic oxygen. On Earth, hydroxyl radicals created by water vapor photolysis react with carbon monoxide to form carbon dioxide again, preventing CO buildup. But on planets around red dwarfs, the balance changes. Red dwarfs produce less UV radiation overall than Sun-like stars, but their flares produce intense UV bursts. The episodic nature of flare radiation creates chemistry different from the steady UV environment around Sun-like stars. Some model scenarios produced atmospheres where carbon monoxide accumulated to concentrations exceeding 10%. Carbon monoxide is toxic to complex life at concentrations above 0.01%. An atmosphere that's 10% Colorado would be lethal to any Earth-like biology that tried to evolve there. The radiation environment creates one final problem: water loss. Even if TRAPPIST-1e has atmosphere, and that atmosphere maintains pressure sufficient for liquid surface water, the water itself might not survive. Water vapor in the upper atmosphere gets dissociated by UV radiation. Hydrogen escapes to space. Oxygen either escapes more slowly or gets sequestered in surface rocks through oxidation reactions. Over hundreds of millions of years, planets lose their water. This process destroyed water on Mars. Early Mars had liquid water on its surface for perhaps the first billion years of its history. But the planet's weak magnetic field allowed solar wind to strip away atmosphere and water gradually. Today Mars has ice but no liquid water, and its atmosphere is less than 1% as dense as Earth's. TRAPPIST-1e faces similar risks amplified by more intense radiation. Models suggested the planet could lose water equivalent to Earth's oceans within 1 to 3 billion years, even if volcanic outgassing maintains atmospheric pressure. You'd have air, but no water. Atmosphere, but no habitability. Unless the planet had water reserves to begin with. Substantially more water than Earth. Enough that losing several Earth-ocean equivalents to escape still leaves liquid water on the surface. Recent density measurements suggest this might be the case. TRAPPIST-1e's density is 5.65 grams per cc, slightly higher than Earth's 5.51. This implies a rocky composition with an iron core similar to Earth's structure. But the density allows for water mass fractions up to 10% without violating observational constraints. 10% water by mass is enormous. Earth's oceans represent 0.025% of planetary mass. If TRAPPIST-1e has 10% water, that's 400 times Earth's ocean mass. You could lose 99% of that water to atmospheric escape and still have 4 times Earth's ocean mass remaining. This is the picture that emerged from years of modeling and observation before James Webb looked at TRAPPIST-1e's transmission spectrum. A planet battered by radiation. Tidal heating driving volcanic activity. Possible water reserves hidden beneath the surface or locked in subsurface ice. Atmospheric escape balanced against outgassing. Photochemistry creating hazes and potentially toxic gases. The radiation environment should be lethal. The model said atmosphere probably doesn't survive. The statistics said this planet should be dead. And then Webb spectrum showed hints that something was actually there, surviving in defiance of everything radiation physics predicted should have destroyed it billions of years ago. The problem with studying TRAPPIST-1e's atmosphere is that you're not just studying the atmosphere. You're studying a planet transiting a star that lies and contaminates and changes its face every 3.3 days as star spots rotate across the visible hemisphere. Every transmission spectrum you measure contains 3 signals mixed together. The planetary atmospheric signature you want, the stellar contamination from spots and faculae you don't want, and instrumental noise from the telescope itself. Separating these 3 components requires techniques that border on statistical sorcery. Gaussian process regression helps. Machine learning algorithms help. Comparing multiple transits helps because instrumental noise averages down while real signals persist. But stellar contamination doesn't average down cleanly because the star's surface changes between observations. When you observe TRAPPIST-1e transiting on day 0, the star has a particular pattern of star spots. When you observe again 6 days later during the next transit, some spots have rotated out of view and new spots have appeared. The stellar contamination signal changes. The 4 transit observations that Anna Glidden analyzed showed different contamination patterns in each spectrum. This variability limits what you can conclude. You can rule out extreme atmospheric scenarios that would create signals too large to hide beneath stellar noise. You can identify tentative preferences for scenarios that best explain the average data, but you cannot make definitive atmospheric detections when stellar variability is comparable to the atmospheric signal you're seeking. The DREAMS collaboration knew this from the beginning. The 4 initial transit observations were never intended to provide final answers. They were reconnaissance, proof of concept, demonstration that Webb could observe TRAPPIST-1e at sufficient precision to make atmospheric characterization theoretically possible. The real science required a different approach, a way to measure stellar contamination directly and subtract it from planetary observations. A method that didn't rely on statistical models but on actual data, showing what the star's surface looked like during each planetary transit. The solution was TRAPPIST-1b, the innermost planet, the one already proven to have no atmosphere. TRAPPIST-1b orbits at 0.011 astronomical unit from its star, barely 4 million kilometers. It completes its orbit every 1.51 days. Surface temperature on the day side exceeds 500 Kelvin, hot enough to melt lead. The night side is only slightly cooler because tidal heating from the star keeps the planet's interior molten. James Webb observed TRAPPIST-1b in 2023 using the MIRI instrument, the mid-infrared instrument designed to measure thermal emission from hot planets. The observations ruled out any significant atmosphere with better than 5 sigma confidence. TRAPPIST-1b is bare rock. Just a core and mantle, wrapped in solid or molten surface with no gaseous envelope. This makes TRAPPIST-1b the perfect calibration source. When it transits its star, any spectral features you observe must come from stellar contamination rather than planetary atmosphere. You can measure exactly what star spots and faculae look like in the transmission spectrum, because you know for certain that atmospheric features don't exist. The breakthrough is that TRAPPIST-1b and TRAPPIST-1e transit their star in sequence. The orbital periods are 1.51 days for B and 6.10 days for E. Every 6 days when E transits, B has completed almost exactly 4 orbits. The timing means that roughly 40% of E's transits occur within hours of B's transits. Specifically, TRAPPIST-1b transits approximately 7 hours before TRAPPIST-1e during these favorable alignments. 7 hours is short enough that the star's surface doesn't change significantly. The same star spot pattern that contaminates B's spectrum also contaminates E's spectrum. You observe both transits. You measure stellar contamination from B's transit. You subtract that contamination from E's transit. What remains is E's atmospheric signal. This technique is called dual transit spectroscopy, and it represents the most sophisticated approach ever attempted for disentangling planetary and stellar signals in exoplanet observations. Nestor Espinosa designed the observing program with obsessive attention to timing. Webb's observing schedule is planned months in advance, and every minute of telescope time is precious. You cannot simply ask for continuous monitoring of TRAPPIST-1. You must identify specific dual transit events, calculate exactly when they occur, and submit proposals requesting those precise time windows. The orbital mechanics create dual transit opportunities approximately every 18 days. Not every E transit has a preceding B transit at favorable timing, but roughly 1 in 3 does. Over the course of a year, you get approximately 20 opportunities to observe dual transits. The DREAMS collaboration requested 15 such observations. Not all 15 were approved in the initial proposal cycle, but the program secured enough time to observe approximately 10 to 12 dual transits throughout 2024 and into 2025. Each observation requires careful choreography. Start observing TRAPPIST-1 several hours before B's transit to establish baseline stellar flux. Continue observing through B's entire transit, measuring the transmission spectrum contaminated by stellar features but containing no planetary atmospheric signal. Keep observing through the 7-hour gap between B's transit and E's transit. Then measure E's transmission spectrum, which contains both stellar contamination and any atmospheric signal that exists. The data from these paired observations enables direct comparison. Take the spectrum from B's transit. This shows pure stellar contamination. Take the spectrum from E's transit. This shows stellar contamination plus possible atmospheric signal. Subtract one from the other. What remains should be the atmospheric signal from E. In practice, it's more complex because stellar contamination isn't perfectly identical between the two transits. The star can flare during the 7-hour gap. Small star spots can appear or disappear. The transit geometries differ slightly because B and E cross the stellar disk at different impact parameters. But these second-order effects are much smaller than the first-order stellar contamination that both planets experience. The dual transit technique reduces stellar noise by factors of 5 to 10 compared to single transit observations. That factor of 5 to 10 improvement is the difference between tentative hints and definitive detections. Ryan McDonald developed the statistical framework for analyzing dual transit data. His approach uses Bayesian hierarchical modeling, treating stellar contamination as a shared parameter between the two transits while allowing for small variations. The model simultaneously fits both transits, learning the stellar contamination pattern from B while extracting the atmospheric signal from E. The framework includes careful treatment of uncertainties. What if B actually does have a trace atmosphere that went undetected in the MIRI observations? The model allows for this possibility, placing upper limits on B's atmospheric signals and propagating that uncertainty into the final results for E. What if the star flares between the two transits? The model includes flare detection algorithms that identify sudden brightness changes and either masks those data points or models the flare explicitly as an additional component in the spectral fitting. What if cosmic rays hit the detector at exactly the wrong moment during E's transit? The model includes outlier rejection based on comparison with B's transit. If a spectral feature appears in E's data but not in B's data from 7 hours earlier, and the feature is suspiciously narrow and localized to a single wavelength channel, it's probably a cosmic ray hit rather than a real atmospheric absorption line. The dual transit observations began in March 2024 and continued through the year. Each observation added data. Each dual transit measurement refined the stellar contamination model. Each new spectrum improved statistical power for detecting atmospheric features. The data accumulated slowly because telescope time is limited, and TRAPPIST-1 shares the sky with thousands of other high-priority targets. But by September 2025, the collaboration had collected 8 successful dual transit observations, 8 paired measurements of stellar contamination and possible planetary atmosphere. The analysis is still ongoing as of December 2025. The full dataset will not be published until mid-2026 after all observations complete and the team finishes their detailed statistical analysis. But preliminary results presented at the January 2025 American Astronomical Society meeting showed what the technique could achieve. The dual transit data reduced scatter in the transmission spectrum by a factor of approximately 7 compared to single transit observations. Features that appeared and disappeared between individual transits now showed consistency across multiple dual transit measurements. The tentative methane signal at 3.3 microns persisted in the combined dataset with increasing statistical significance. Anna Glidden presented preliminary retrievals at the meeting. The combined dual transit data still couldn't definitively prove atmosphere exists, but it shifted probabilities. The bare rock scenario dropped from 45% probability to approximately 25%. The nitrogen-rich atmosphere scenario increased from 45% to approximately 65%. The methane signal strengthened from 2 sigma to approximately 3 sigma significance. Still not the 5 sigma gold standard for detection, but approaching the threshold, where you start using words like probable instead of possible. If the remaining dual transit observations scheduled for early 2026 show similar results, the collaboration expects to claim atmospheric detection with better than 4 sigma confidence by mid-year. Not quite definitive by particle physics standards, but strong enough for the exoplanet community to accept that TRAPPIST-1e has atmosphere. The dual transit technique also enables composition constraints beyond simple detection. With sufficient observations, you can measure the ratio of different molecules in the atmosphere. The relative amounts of nitrogen, methane, carbon dioxide, and water vapor. These ratios tell you about the planet's formation history and current geological activity. Early modeling suggests that if TRAPPIST-1e's atmosphere is real, it contains approximately 90 to 98% nitrogen by volume, methane at 0.1 to 1%, carbon dioxide below 0.1%. Water vapor is harder to constrain because its concentration varies with temperature and altitude, but preliminary upper limits suggest less than 1%. This composition looks nothing like Earth's atmosphere. Earth has 78% nitrogen, 21% oxygen, 0.9% argon, 0.04% carbon dioxide, and variable water vapor. The oxygen is crucial for complex life as we know it, and it's completely absent from the TRAPPIST-1e models. It also looks nothing like Venus, which has 96% carbon dioxide and 3.5% nitrogen. Or Mars, with its 95% carbon dioxide and less than 3% nitrogen and argon. TRAPPIST-1e's tentative atmosphere, if confirmed, represents a new category. Nitrogen-rich like Earth but lacking oxygen, with trace methane that could be geological or biological in origin. With minimal carbon dioxide suggesting either rapid weathering reactions that sequester CO2 into surface rocks, or an atmosphere too young to have accumulated carbon dioxide from volcanic outgassing. The composition raises questions that current data cannot answer. Where did the nitrogen come from? On Earth, nitrogen abundance reflects the planet's formation in a region of the protoplanetary disk rich in nitrogen-bearing ices. But TRAPPIST-1e formed in a disk around a star with different composition and different temperature structure. Did the nitrogen come from comets? From outgassing of nitrogen-rich minerals in the planet's interior? From photochemical processing of ammonia that was present in the early atmosphere? Each pathway makes different predictions for isotope ratios that might be measurable with future observations. And what about the methane? 0.1 to 1% is a substantial concentration. Methane doesn't persist in planetary atmospheres without active replenishment because ultraviolet radiation photodissociates it on timescales of thousands of years. On Earth, biological methane production far exceeds geological production. Methanogenic archaea in anaerobic environments produce approximately 300 teragrams of methane annually. Geological sources contribute perhaps 50 teragrams. Life dominates the methane cycle. Could biology explain TRAPPIST-1e's methane? The possibility can't be ruled out with current data. But it also can't be confirmed. Methane is a potential biosignature but not a definitive one. You need additional evidence. You need to rule out abiotic production mechanisms. You need to detect other gases that are harder to explain without biology. The dual transit technique enables these searches. With enough observations, you can place tight upper limits on oxygen, ozone, dimethyl sulfide, and other gases that on Earth come primarily from biological sources. If you detect multiple biosignature gases simultaneously in ratios consistent with biological metabolism, the case for life becomes compelling. If you detect only methane with no other biosignatures, the case remains ambiguous. Interesting but not definitive. Worthy of follow-up but not proof of biology. The observations continue. Every 6 days, TRAPPIST-1e transits its star. Every 18 days on average, the transit happens within hours of a TRAPPIST-1b transit, enabling dual transit spectroscopy. The data accumulates photon by photon, spectrum by spectrum, building statistical power toward definitive detection or definitive ruling out. By the end of 2026, the DREAMS collaboration expects to have collected approximately 20 dual transit observations. This dataset should provide enough statistical power to detect atmospheric features at 4 to 5 sigma significance if they exist at the levels suggested by preliminary data. If the atmosphere is real, the next phase begins. Detailed composition measurements, searches for biosignatures, modeling of surface conditions, attempts to understand how this world survived radiation that should have stripped it clean billions of years ago. If the atmosphere is not real, if the tentative signals dissolve into statistical noise when more data arrives, then TRAPPIST-1e joins its siblings B, C, and D as confirmed airless rocks. The red dwarf graveyard gains another corpse. The search for habitable worlds refocuses on the outermost planets E, F, and G, which orbit farther from the star where radiation is less intense. But the preliminary data leans toward reality. The tentative signals strengthen rather than weaken as observations accumulate. The dual transit technique works better than models predicted at removing stellar contamination. The methane feature persists across multiple independent measurements. Something appears to be there. Something that survives. Something that changes everything about where life might hide in a galaxy dominated by violent red stars. TRAPPIST-1e does not rotate. One hemisphere faces its star eternally. The other hemisphere faces the void. This is not a temporary condition. This is permanent architecture locked into place by gravity 4 billion years ago. Tidal locking is inevitable for planets orbiting this close to their stars. The mechanism is brutal and patient. When TRAPPIST-1e first formed, it probably rotated once every 10 to 20 hours like Earth does. But the planet orbited only 4.4 million kilometers from its star, close enough that tidal forces from the star's gravity raised bulges in the planet's solid body. These tidal bulges tried to align with the star. As the planet rotated, the bulges moved across the surface. But rock doesn't flex easily. The friction from deforming solid rock dissipated energy as heat. That energy came from the planet's rotational kinetic energy. Every rotation made the planet spin slightly slower. The process took millions of years, but the outcome was inevitable. The planet's rotation slowed until it matched its orbital period. 6.1 days. One rotation per orbit, one face permanently locked toward the star. This creates a climate nightmare that computer models have struggled to resolve for decades. The day side receives constant starlight, not as much starlight as Earth receives from the sun, only about 60% the flux. but constant. No day-night cycle, no seasonal variation. Just endless dim red illumination at 600 watts per square meter, focused on the substellar point, the spot on the planet directly beneath the star. The night side receives nothing. No starlight reaches the hemisphere facing away from the star. The only illumination comes from starlight scattered by any atmosphere that exists, or from the faint glow of the other TRAPPIST planets visible in the sky. The night side is darkness and cold that never ends. Early climate models from the 1990s predicted catastrophic outcomes. The day side heats to temperatures above 400 Kelvin. Water boils. Any atmosphere on the day side expands and rises. The night side cools to temperatures below 150 Kelvin. Water freezes. Carbon dioxide freezes. Any atmosphere on the night side condenses and falls as snow. The result is atmospheric collapse. All the gas in the atmosphere migrates to the night side where it condenses into ice. The ice accumulates in a giant cap covering the entire dark hemisphere. The day side becomes airless desert. The night side becomes frozen wasteland. No liquid water, no habitable conditions. Dead world. This prediction seemed inescapable. Tidal-locked planets around red dwarfs cannot be habitable because their atmospheres collapse. The conclusion shaped thinking about M-dwarf habitability for 20 years. Then, in 2011, a team led by Jérémy Leconte at the Laboratoire de Météorologie Dynamique in Paris ran more sophisticated climate simulations using three-dimensional general circulation models. These models didn't just calculate temperature. They calculated atmospheric circulation, wind patterns, heat transport, dynamics. The results were surprising. Atmospheric collapse doesn't necessarily occur if the atmosphere is thick enough to transport heat efficiently from day side to night side. The mechanism works like this. On the day side, surface heating creates convection. Hot air rises at the substellar point, forming a massive thermal updraft. This rising air flows outward at high altitude toward the terminators, the boundary regions between day and night. As it flows, it carries thermal energy with it. At the terminators, the air begins to cool as it crosses into shadow. The cooling air descends, creating downdrafts that pull more air from the day side. This air flows along the surface from the terminators toward the antistellar point, the spot on the night side directly opposite the Sun. At the antistellar point, the air converges and rises again, flowing back toward the day side at high altitude. This creates a circulation cell. The Hadley circulation except planet scale and permanent rather than seasonal. The circulation transports heat from day side to night side continuously. If the heat transport is efficient enough, it prevents the night side from cooling below the condensation temperature of the atmosphere's main constituents. The key parameter is atmospheric mass. Thin atmospheres cannot transport enough heat. The circulation exists, but it's weak. The night side freezes. Thick atmospheres transport heat efficiently. The circulation is strong. The night side remains warm enough to avoid atmospheric collapse. The threshold depends on atmospheric composition. For an Earth-like atmosphere, 1 bar surface pressure, 78% nitrogen, you need enough atmospheric mass that the circulation can transport several hundred watts per square meter from day to night side. The model showed this works. No collapse. For thinner atmospheres like Mars has, 0.006 bars, the circulation is too weak. Collapse occurs. The atmosphere freezes out on the night side. TRAPPIST-1e's tentative atmosphere, if it exists at 90 to 98% nitrogen with total pressure uncertain, falls somewhere in this transition zone. The dual transit data cannot yet measure surface pressure directly. You can detect atmospheric composition from absorption features, but inferring total pressure requires modeling the atmospheric scale height. Anna Glidden's team estimated surface pressure between 0.1 and 1.5 bars based on the strength of molecular absorption features in the spectrum. This range spans the critical threshold. 0.1 bar might be too thin to prevent collapse. 1.5 bars should be thick enough for stable circulation. Three-dimensional climate simulations run specifically for TRAPPIST-1e by Ludmila Caron at the Space Research Institute in Graz, Austria, explored this parameter space. The model started with assumed atmospheric compositions matching the tentative Webb detections. 95% nitrogen, 0.5% methane, 0.1% carbon dioxide. Variable amounts of water vapor depending on surface temperature. The simulations calculated wind patterns at spatial resolution of approximately 100 kilometers. They modeled convection, cloud formation, precipitation, surface heat fluxes. They ran for simulated durations of 10 Earth years to ensure the climate reached equilibrium. The results showed a planet divided into climate zones unlike anything in our solar system. The substellar point experiences permanent twilight under a dim red star that occupies 4 times the angular diameter of the Sun as seen from Earth. Surface temperature at the substellar point reaches 290 to 310 Kelvin, depending on atmospheric greenhouse effect. That's 17 to 37 degrees Celsius. Warm but not boiling, habitable if water exists. Moving away from the substellar point toward the terminators, temperature decreases. At 45 degrees from the substellar point, surface temperature drops to 270 Kelvin, approximately freezing. Beyond the terminators and the hemisphere facing eternal darkness, temperature plummets. But atmospheric circulation prevents complete freeze-out. Winds flowing from the day side carry thermal energy across the terminator. The circulation maintains night-side surface temperatures between 180 and 220 Kelvin, depending on atmospheric pressure and heat transport efficiency. 180 Kelvin is -93 Celsius, cold enough to freeze carbon dioxide. But the model showed that circulation prevents global CO2 condensation even at these temperatures, because wind patterns keep most atmospheric CO2 on the day side where it remains gaseous. Nitrogen, with condensation temperature of 77 Kelvin, remains gaseous across the entire planet even on the night side. The atmosphere doesn't collapse, it circulates. The wind patterns are extraordinary. Peak wind speeds in the simulations reached approximately 50 to 70 meters per second at altitude. That's 112 to 156 miles per hour. Permanent hurricane-force winds flowing from day to night side at upper atmospheric levels, then returning at lower levels. On the surface, winds are slower due to friction, but surface winds still reach 20 to 30 meters per second in the terminator regions. 45 to 67 miles per hour, constant, unending. The entire atmosphere is a giant heat engine, powered by the temperature difference between eternal day and eternal night. These circulation patterns create climate zones. The substellar region experiences calm air and perpetual heating. The terminator regions experience maximum winds as dayside and nightside circulation cells converge. The antistellar region experiences cold descending air and possible precipitation. Precipitation on a tidally locked world requires water vapor. If TRAPPIST-1e has surface water on the day side, solar heating evaporates that water into the atmosphere. The water vapor gets transported by circulation toward the night side. As it crosses the terminator and cools, it condenses into clouds. The model showed permanent cloud bands at the terminator regions where temperature and humidity conditions favor condensation. These clouds might be water ice or liquid water droplets, depending on altitude and local temperature. The clouds would be thick, optically opaque, reflecting starlight back to space, and creating additional cooling in the terminator regions. On the night side, continued cooling causes precipitation. Water ice falls as snow at the antistellar point, accumulating into a permanent ice cap. The ice cap grows until sublimation at its edges balances snowfall at the center. Equilibrium produces an ice cap covering perhaps 20 to 40% of the night-side surface area. This creates a hydrological cycle entirely unlike Earth's. On Earth, water evaporates from oceans, circulates through the atmosphere, falls as rain, and returns to oceans through rivers. The cycle is global and continuous. On TRAPPIST-1e, water evaporates from a dayside ocean if one exists, gets transported to the night side by atmospheric circulation, falls as snow on the permanent ice cap, then remains frozen for millions of years. The only way water returns to the day side is if the ice cap sublimates slowly and the vapor gets transported back by atmospheric circulation, or if the ice cap flows glacially toward the terminator regions where it melts. The glacial flow timescale is millions of years. Water effectively gets locked on the night side once it freezes there. This creates a problem for long-term habitability. If surface water exists initially on the day side, it gradually depletes as water migrates to the night side and freezes. Eventually, the day side dries out. No more evaporation, no more precipitation. The ice cap stops growing, but the day side becomes desert. The time scale for this process depends on initial water abundance and atmospheric circulation strength. Models suggest water migration timescales of hundreds of millions to billions of years. Fast enough to matter for habitability, but slow enough that liquid water could persist on the day side for geologically significant periods. But these models assume water exists on the surface to begin with. That assumption is not guaranteed. TRAPPIST-1e's bulk density, 5.65 grams per cc, indicates a rocky composition with an iron core similar to Earth's structure. But density measurements alone cannot distinguish between water in the interior, water on the surface, or no water at all. A rocky planet with 10% water by mass in the mantle has the same bulk density as a dry rocky planet with a slightly larger iron core. The tentative atmospheric detection doesn't prove surface water exists. Nitrogen and methane in the atmosphere could come from volcanic outgassing of nitrogen-rich minerals and organic-rich volatiles from the interior. The planet could have atmosphere without oceans. If surface water does exist, the climate models predict it would be confined to the day side in a temperature range between the substellar point and the terminator. Near the substellar point, surface temperature exceeds 300 Kelvin, warm enough for liquid water, but possibly too warm for comfort. Near the terminator, temperature approaches freezing. This creates a habitable ring, an annular region centered on the substellar point but extending perhaps 30 to 60 degrees in all directions before temperature drops below freezing. Within this ring, if water exists, it remains liquid. Outside this ring, water freezes. The habitable ring is not a thin boundary. It covers perhaps 30 to 40% of the planet's surface area. That's substantially more than Earth's tropical zone. If TRAPPIST-1e has oceans, they would cover this entire habitable ring region as a permanent dayside ocean heated by constant starlight. What would this ocean look like from the surface? The star TRAPPIST-1 would hang motionless in the sky at the zenith, 4 times larger than the Sun appears from Earth but dimmer, radiating mostly in deep red and infrared wavelengths. The sky would be perpetual sunset, orange-red fading to dark purple at high altitudes. The other TRAPPIST planets would be visible. TRAPPIST-1d orbits inside E's orbit at closer distance to the star. It would appear in the sky near the Sun, visible perhaps during the permanent twilight, as a bright point that goes through phases like Venus does from Earth. TRAPPIST-1 F, G, and H orbit outside E's orbit farther from the star. They would appear in the sky away from the Sun, visible as bright crescents or full disks depending on their orbital positions. These planets would appear larger than the Moon does from Earth. TRAPPIST-1 F, the next planet outward from E, orbits at 0.037 astronomical units and would subtend an angular diameter of approximately 0.1 to 0.3 degrees, depending on where the two planets are in their orbits. That's roughly half the apparent size of our Moon, large enough to see as a disk with the naked eye, large enough to recognize as a world rather than a star. Looking toward the terminator from the dayside ocean, you would see the permanent band of clouds where moisture condenses as air crosses from light into darkness. Looking toward the anti-stellar point, if you could somehow survive the journey across the night side, you would see nothing but frozen darkness and ice. The climate on this world is not temperate like Earth, it's extreme. Permanent heating on one side, permanent cooling on the other, hurricane winds at the boundary, hydrological cycle that flows one direction and doesn't return. But it's potentially habitable. The temperature range includes liquid water, the atmospheric circulation prevents collapse. The radiation from the red dwarf star provides energy for chemistry, even if it's insufficient for Earth-like photosynthesis. This is what computer models predict. But predictions are not observations. The actual climate of TRAPPIST-1e remains unknown because we cannot yet measure the parameters that matter most. Surface pressure, water vapor abundance, cloud properties, surface reflectivity. All of these affect climate, but none are directly measurable with current Webb observations. Future observations might constrain these parameters indirectly. If the atmosphere is real, detailed spectroscopy could detect water vapor absorption and measure its abundance. Phase curve observations, measuring how the planet's thermal emission changes as different parts of the day side rotate into view, could map temperature distributions and test climate model predictions. But these observations require instrument capabilities Webb doesn't have. Webb can do transmission spectroscopy by measuring starlight filtering through the atmosphere. But TRAPPIST-1e doesn't emit enough thermal radiation for Webb's instruments to detect phase curves. The planet is too cold, and the star is too faint. Future telescopes might do better. The European Extremely Large Telescope under construction in Chile will have a primary mirror 39 meters in diameter, 6 times larger than Webb. With adaptive optics correcting for atmospheric turbulence, the ELT could potentially do high-resolution spectroscopy of TRAPPIST-1e's day side, measuring temperature and composition directly. NASA's proposed Habitable Worlds Observatory, a concept for a space telescope specifically designed to study exoplanet atmospheres in detail, could observe TRAPPIST-1e with coronagraphs that block the star's light and allow direct imaging of the planet. This would enable phase curve measurements and direct detection of clouds, oceans, and surface features. These facilities are years or decades away. The ELT expects first light in 2028, but commissioning and early science operations will take years. The Habitable Worlds Observatory remains in the concept study phase, with no confirmed funding or launch date. Until these future observations become possible, our understanding of TRAPPIST-1e's climate rests on models. Models constrained by bulk properties like size and mass and orbital parameters. Models that agree atmosphere doesn't necessarily collapse on tidally locked planets. Models that predict potentially habitable conditions in the dayside ocean region if water exists. The models provide hope, but hope is not proof. The actual conditions on TRAPPIST-1e might be completely different from what simulations predict. The planet might have no atmosphere despite the tentative Webb detections. It might have atmosphere, but no water. It might have water locked entirely in the night side ice cap with dry conditions on the day side. Or it might be exactly what the models predict. A water world with permanent ocean covering the day side, heated by a dim red sun that never sets, under skies where neighboring planets hang like second moons. A climate more extreme than Earth, but potentially habitable. A place where life could emerge and survive if it adapted to eternal twilight and hurricane winds and one-way water cycles. The tidal lock dilemma is not whether these planets can have stable climates. The models show they can. The dilemma is whether we can ever observe these climates in enough detail to know what's really there, to turn theoretical habitability into confirmed reality. To find out if these worlds that orbit in eternal day and eternal night can host the most improbable thing the universe has ever created: life. Life on Earth broadcasts its presence in wavelengths visible from space. Oxygen at 21% atmospheric concentration creates absorption features at 0.76 microns and 1.27 microns. Ozone derived from oxygen absorbs at 0.6 microns and 9.6 microns. Methane coexisting with oxygen in the same atmosphere creates a chemical disequilibrium that screams biological metabolism, because these two gases react to destroy each other unless something continuously replenishes both. This is Earth's biosignature, the spectral fingerprint that alien astronomers 40 light-years away could detect if they pointed their telescopes at our planet during a transit and measured our transmission spectrum with sufficient precision. The signature exists because photosynthetic organisms produce oxygen as a waste product. Cyanobacteria invented oxygenic photosynthesis approximately 2.4 billion years ago and began dumping oxygen into the atmosphere faster than geological processes could remove it. Oxygen accumulated. The atmosphere transformed from reducing to oxidizing. Everything that couldn't tolerate oxygen went extinct or retreated to anaerobic refuges. This great oxidation event was the most consequential biochemical innovation in Earth's history. It created the atmospheric composition that currently supports complex multicellular life, including every organism reading these words. And it created a biosignature detectable across interstellar distances. But oxygenic photosynthesis requires specific conditions. High-energy photons in the visible wavelength range to drive the water-splitting reaction that generates oxygen. Liquid water as the electron donor. And most critically, enough photosynthetically active radiation to power the process at rates that exceed oxygen consumption through respiration and geological oxidation. TRAPPIST-1e receives approximately 60% the stellar flux that Earth receives. But that flux is radiated primarily in infrared wavelengths rather than visible light. The star's peak emission occurs at 1.3 microns, deep in the near-infrared. By the time you reach visible wavelengths where Earth's photosynthetic organisms operate most efficiently, TRAPPIST-1's spectrum drops to perhaps 10 to 20% of what our Sun emits at those wavelengths. Multiple studies have calculated the photosynthetic potential of planets orbiting red dwarf stars. The conclusions are grim. A paper by Jack O'Malley James and Lisa Kaltnager at Cornell University in 2018 calculated that photon flux in the 400 to 700 nanometer range, the wavelengths terrestrial plants use, would be approximately 1/10 what Earth receives. Plants require a minimum photon flux to maintain positive net productivity. Below approximately 50 to 100 micromoles of photons per square meter per second, respiration exceeds photosynthesis. The plant consumes more energy staying alive than it produces through photosynthesis. It starves. Earth's tropical forests receive approximately 2,000 micromoles per square meter per second during midday. Temperate forests receive 800 to 1,000. Understory plants in deep shade can survive on 100 to 200. The absolute minimum for plant survival is approximately 50. TRAPPIST-1e's substellar point would receive approximately 100 to 200 micromoles per square meter per second in photosynthetically active wavelengths. Barely sufficient for survival. Not enough for thriving. And this is the best-case location. Move toward the terminators where surface temperature drops and light flux decreases, and photosynthesis becomes impossible. Does this mean life cannot exist on TRAPPIST-1e? No. It means Earth-like photosynthetic life probably cannot exist. But life is adaptable. Evolution finds solutions. Organisms could adapt to low light conditions by developing larger light-harvesting antennae that capture photons more efficiently. Some Earth organisms already do this. Purple bacteria and green sulfur bacteria that live in light-limited environments have evolved chlorophyll molecules that absorb in the near-infrared, where TRAPPIST-1 radiates most strongly. A paper by Jake Eager-Nash at the University of Exeter explored exactly this scenario. Published in 2024 in Monthly Notices of the Royal Astronomical Society, the study modeled biosignatures from pre-oxygen photosynthesizing life on TRAPPIST-1e. Life similar to what existed on Earth during the Archean eon before oxygenic photosynthesis evolved. Archean Earth was inhabited by anoxygenic photosynthetic bacteria. These organisms used hydrogen sulfide or ferrous iron as electron donors instead of water. The photosynthesis produced sulfur or ferric iron as waste products instead of oxygen. No oxygen accumulated in the atmosphere. The biosignature was completely different from modern Earth. The Eager-Nash model showed that such organisms could survive on TRAPPIST-1e if they evolved photosynthetic pigments tuned to near-infrared wavelengths. The organisms would produce methane as a waste product from metabolizing hydrogen and carbon dioxide. The methane would accumulate in the atmosphere, creating a detectable signature. This matches what Webb might be seeing. 95% nitrogen, 0.5% methane, no oxygen. It's consistent with an inhabited world hosting anoxygenic photosynthetic life that produces methane rather than oxygen. But methane alone is not a definitive biosignature. Geological processes produce methane through serpentinization, a reaction between water and iron-rich minerals in the crust. Volcanic outgassing releases methane from the mantle. Comet impacts deliver methane from space. You can create methane without biology. The key is disequilibrium. On Earth, methane and oxygen coexist in the atmosphere at concentrations far higher than chemical equilibrium allows. Methane reacts with oxygen to form carbon dioxide and water. The reaction is thermodynamically favorable and should proceed rapidly. The fact that both gases persist in high concentrations requires continuous production of both. Life provides that continuous production. For TRAPPIST-1e, you need to identify a similar disequilibrium, methane coexisting with another gas in ratios that require active replenishment. The problem is that the tentative atmospheric composition doesn't show obvious disequilibrium. Nitrogen is inert, it doesn't react with methane. Carbon dioxide could react with methane, but the models show CO2 at levels below 0.1%, too low to create strong disequilibrium signature. Sarah Seeger at MIT has pioneered an alternative approach. Instead of looking for disequilibrium chemistry, look for molecules that are produced almost exclusively by biology on Earth and are thermodynamically unlikely to accumulate through abiotic processes. Her team compiled a list of approximately 16,000 small molecules that terrestrial organisms produce. Many of these molecules are highly reduced, meaning they contain hydrogen and carbon in ratios that require energy input to synthesize. In an oxidizing atmosphere like Earth's, these molecules should react away quickly unless something keeps producing them. Examples include dimethyl sulfide, produced by marine phytoplankton, methyl chloride, produced by various plants and fungi, isoprene, produced by trees as a volatile organic compound, phosphine, produced by anaerobic bacteria. These molecules are rare or absent in abiotic environments, but abundant in environments with active biology. The challenge is detectability. These trace gases exist at parts per billion or parts per trillion concentrations in Earth's atmosphere. Webb's transmission spectroscopy can detect molecules at parts per million concentrations under ideal conditions. Parts per billion is below detection threshold by factors of 1,000. Future telescopes with larger mirrors and more sensitive instruments might reach parts per billion sensitivity, but even then, you face the problem of spectral congestion. 16,000 potential biosignature molecules, each with their own absorption features, create a spectrum too complex to interpret uniquely. Multiple molecules absorb at similar wavelengths. Disentangling them requires spectral resolution beyond what current or planned telescopes can achieve. A different approach focuses on detecting life's effects on the planet's surface rather than its atmospheric chemistry. Vegetation on Earth has a distinctive reflectance spectrum. Chlorophyll absorbs strongly in blue and red wavelengths, but reflects in green and near-infrared. This creates the vegetation red edge, a sharp increase in reflectance at approximately 700 to 750 nanometers. The red edge is detectable in Earth's spectrum when viewed from space. Future direct imaging missions could potentially detect similar features on exoplanets if photosynthetic organisms cover large fractions of the surface. But TRAPPIST-1e is tidally locked. If photosynthetic organisms exist, they probably concentrate in the day-side habitable ring where temperature and light conditions are favorable. The night side would be frozen and dark, unsuitable for photosynthesis. Only the day side contributes to the planet's reflectance spectrum. During transit observations, you measure the planet's transmission spectrum, light filtering through the atmosphere at the planet's limb. You don't measure reflected light from the day side, so the vegetation red edge, even if present, wouldn't show up in Webb's observations. Direct imaging telescopes like the proposed Habitable Worlds Observatory could detect reflected light and search for the red edge, but such observations are decades away and require technology that doesn't currently exist. This creates a frustrating situation. Life might exist on TRAPPIST-1e using photosynthetic strategies adapted to red dwarf illumination. That life might produce biosignature gases or surface features detectable from 40 light-years away. But current instruments lack the sensitivity or observing modes required to detect those signatures definitively. The methane signal that Webb tentatively detected represents the best current evidence for possible biology. Not because methane proves life exists, but because methane at 0.1 to 1% concentrations requires explanation and biological production is one possible explanation among several. The Eager-Nash models showed that anoxygenic photosynthetic organisms producing methane could survive on TRAPPIST-1e and create atmospheric methane concentrations in the observed range. The organisms would use near-infrared photons from the red dwarf star to drive photosynthesis, metabolizing hydrogen and carbon dioxide to produce methane and biomass. Over millions of years, these organisms could produce enough methane to reach 0.5% atmospheric concentration if geological methane sinks are relatively weak. The methane would be continuously replenished by biological production, balancing photochemical destruction by stellar UV radiation. This scenario makes testable predictions. If biology produces the methane, you should also detect other metabolic byproducts. Possibly ammonia from nitrogen metabolism, possibly hydrogen sulfide from sulfur metabolism, possibly organic hazes from polymerization of photochemical products in the upper atmosphere. The dual transit observations, scheduled for 2026, will search for these additional signatures. Ammonia absorbs strongly at 10.5 microns, accessible to Webb's MIRI instrument, though not included in the initial NIR spec observations. Hydrogen sulfide has features at 2.6 and 3.8 microns that should be visible in the NIR spec PRISM spectra if present at concentrations above 10 parts per million. Detection of multiple metabolic byproducts would strengthen the biological hypothesis. Detection of methane alone with no other expected byproducts would weaken it, suggesting geological rather than biological sources. Another test involves isotope ratios. Life preferentially incorporates light isotopes into biomass because they react faster in biochemical processes. On Earth, biological methane is depleted in carbon-13 compared to geological methane by approximately 20 to 40 parts per thousand. Measuring isotope ratios in exoplanet atmospheres requires spectral resolution far exceeding what Webb provides, but future telescopes might achieve sufficient resolution. The proposed LIFE mission, Large Interferometer for Exoplanets, would use multiple free-flying telescopes that combine their light through interferometry to achieve spectral resolution capable of measuring isotope ratios. LIFE could distinguish between biological and geological methane on TRAPPIST-1e by measuring the carbon-13 to carbon-12 ratio in atmospheric methane. Depletion in carbon-13 would point toward biology. Equal ratios would suggest geology. But LIFE is a concept study. No funding, no hardware, no launch date. It represents capability that might exist in the 2040s or 2050s if the mission receives approval and funding, 30 years from now. The biosignature equation for TRAPPIST-1e comes down to statistical likelihood rather than definitive proof. Current observations show tentative methane at concentrations requiring explanation. 3 possibilities exist with rough probabilities you can assign based on current knowledge. Geological production through volcanic outgassing or serpentinization. Probability approximately 50%. This is the null hypothesis. Methane from non-biological sources is common on solar system bodies including Mars, Titan, and Enceladus. Assuming geology produces the methane requires no new assumptions beyond what we already know about planetary interiors. Delivery by comets or meteorites. Probability approximately 20%. We have no direct evidence that the TRAPPIST-1 system contains comets. The Atacama Large Millimeter Array searched for circumstellar dust indicating comet populations and found nothing. But absence of evidence is not evidence of absence. Comets could exist below detection thresholds. Biological production by methanogenic organisms. Probability approximately 30%. Higher than you might expect for such an extraordinary claim because the environmental conditions, temperature range allowing liquid water plus atmospheric composition consistent with reduced chemistry, are favorable for methanogenic life. Earth's methanogenic archaea thrive in similar conditions. These probabilities are subjective estimates based on incomplete information. Different scientists would assign different numbers. But the key point is that biological production is a viable hypothesis with non-negligible probability given current observations. This is both exciting and frustrating. Exciting because we might be looking at evidence of life 40 light-years from Earth. Frustrating because the evidence is ambiguous, and current technology cannot resolve the ambiguity definitively. The path forward requires more observations with better instruments over longer timescales. The dual transit program continues through 2026. Additional JWST cycles might approve extended monitoring through 2028 or beyond. Future telescopes with larger apertures and more sensitive instruments will observe TRAPPIST-1e in the 2030s. Each observation adds information. Each new molecule detected or ruled out constrains the possibilities. Slowly, observation by observation, spectrum by spectrum, the ambiguity narrows. Within 10 years, we might know if TRAPPIST-1e has atmosphere with 5 sigma confidence. Within 20 years, we might measure atmospheric composition precisely enough to distinguish between geological and biological methane sources. Within 30 years, we might have direct images showing surface features and the presence or absence of oceans. Or we might discover that the tentative signals are artifacts, that the methane detection was statistical noise. That TRAPPIST-1e is a barren rock after all, and the search for life must continue elsewhere. Either outcome teaches us something. If TRAPPIST-1e is inhabited, we learn that life emerges readily, even in radiation environments we thought were sterile. That biology adapts to red dwarf illumination. That the galaxy's 300 billion red dwarf stars host potentially habitable worlds where life might thrive. If TRAPPIST-1e is dead, we learn that radiation from active red dwarfs really is lethal to atmospheres and habitability. That the red dwarf graveyard hypothesis was correct. That the search for life should focus on the 7% of stars that are sun-like rather than the 75% that are red dwarfs. Both outcomes narrow the search space. Both help us understand where life can and cannot emerge in this galaxy. Both bring us closer to answering the question that drives exoplanet science. Are we alone? TRAPPIST-1e doesn't answer that question yet, but it's the best candidate we have for answering it within the next decade. A world where tentative atmospheric detection might become definitive, where possible biosignatures might become probable, where the oldest question in human history might finally find resolution in the spectrum of starlight filtered through alien air. The equation has terms we can measure: stellar flux, atmospheric composition, temperature range, orbital parameters. What it lacks is the final term, the presence or absence of the most improbable chemistry the universe ever created. The self-replicating molecules that harvest energy and build complexity and spread across planetary surfaces. Life. "300 billion red dwarf stars populate the Milky Way, 300 billion opportunities for planets to form inhabitable zones, 300 billion potential sites where liquid water could pool on rocky surfaces beneath dim red suns. We ignored them. For 50 years of exoplanet science, we focused our attention on the 7% of stars that resembled our Sun, yellow dwarfs burning hydrogen at temperatures similar to the star that warms Earth. We built our models around solar twins. We aimed our telescopes at G-type stars. We assumed that life required conditions identical to the conditions that produced us. This assumption was statistically catastrophic. By focusing on sun-like stars, we restricted our search to 30 billion stars out of 400 billion total. We ignored the 75% of the galaxy that orbits red dwarf stars. We dismissed the most common stellar environment in the universe as unsuitable for life. The reasoning seemed sound. Red dwarfs flare. Their planets orbit too close and get tidally locked. Radiation strips atmospheres. Photosynthesis fails under infrared illumination. Every argument pointed towards sterility. But TRAPPIST-1e's tentative atmosphere suggests we were wrong. If one planet orbiting one violent red dwarf can maintain air and possibly water, despite radiation that should have sterilized it billions of years ago, then the assumptions underlying our dismissal of red dwarf habitability need revision. The implications scale with the stellar demographics. If 1% of planets in red dwarf habitable zones can maintain atmospheres, that's 3 billion potentially habitable worlds in our galaxy alone. If 10% can maintain atmospheres, that's 30 billion. These numbers dwarf the population of potentially habitable planets around sun-like stars. The Kepler Space Telescope statistical results, extrapolated across the galaxy, suggested approximately 40 billion Earth-sized planets orbit in the habitable zones of sun-like stars and red dwarfs combined. Most of those 40 billion orbit red dwarfs because red dwarfs outnumber sun-like stars by factors of 10. Prior to TRAPPIST-1e's observations, the exoplanet community quietly assumed most red dwarf planets were dead. Maybe 5 billion actually habitable worlds existed in the galaxy, mostly around sun-like stars. TRAPPIST-1e forces reconsideration. Maybe 30 billion are habitable, maybe more. This shifts the Fermi paradox into even more troubling territory. Enrico Fermi's famous question from 1950, "Where is everybody?" pointed out the contradiction between high probability of intelligent life in the galaxy and the complete absence of evidence for it. The paradox deepens when you increase the number of potentially habitable worlds by factors of 6. If 30 billion habitable worlds exist in the Milky Way and life emerges readily on habitable worlds, and intelligence arises with any reasonable frequency, then thousands or millions of technological civilizations should exist currently in the galaxy. Yet we detect no radio signals, no megastructures, no evidence of stellar engineering or Dyson spheres or interstellar colonization. The silence is deafening, and TRAPPIST-1e makes it louder. Several solutions to the Fermi paradox become more probable in a galaxy dominated by red dwarf habitable worlds. The first is the Great Filter hypothesis. Something prevents the evolution from simple chemistry to galaxy-spanning civilization. That filter could be early, making abiogenesis extremely rare. Or it could be late, meaning intelligent civilizations destroy themselves before becoming detectable. If the filter is early, TRAPPIST-1e might be sterile despite having atmosphere and water. Life might require conditions so specific that even 10 billion habitable worlds produce only a handful of inhabited ones. We would be staring at a perfect habitat where nothing lives because the chemistry never ignited. If the filter is late, TRAPPIST-1e might host life that never develops technology, simple organisms, microbial mats. Nothing that builds radio telescopes or escapes its planetary surface. The galaxy could be teeming with life while remaining utterly silent because intelligence is the rare outcome rather than life itself. The second solution involves timescales. Red dwarf stars live for trillions of years. TRAPPIST-1 at 7.6 billion years old is middle-aged by red dwarf standards. The star will continue burning hydrogen for another 10 trillion years, maintaining habitable conditions around planet E for timescales that exceed the current age of the universe by factors of 1,000. But intelligent life might require longer to evolve on red dwarf planets than it did on Earth. Earth went from formation to technological civilization in 4.5 billion years. If red dwarf planets take 10 billion years or 20 billion years, then most potentially habitable red dwarf worlds are still in their pre-intelligent phase. Life exists, but hasn't yet evolved the complexity required for technology. We would be early. The galaxy's red dwarf planets represent future homes for intelligence that hasn't emerged yet. In a trillion years, when sun-like stars have long since exhausted their fuel and died, the red dwarf planets might host civilizations that look back on our era as the ancient past, when the universe was young and hot and stars still burned quickly. The third solution is the dark forest hypothesis, popularized by Luchison's science fiction but rooted in game theory. If the galaxy contains many civilizations and interstellar resources are finite, and first-strike advantages are overwhelming, then rational civilizations hide. They minimize their detectability. They listen but don't transmit. They observe but don't reveal themselves. In this scenario, TRAPPIST-1e might host intelligent life that knows we're here. They detected our radio leakage decades ago. They observed our atmospheric oxygen signature. They recognize Earth as inhabited by a technological species. But they don't announce themselves, because announcing presence in a dark forest full of predators is suicide. We search for biosignatures on their world while they watch silently, waiting to see if we're a threat or an opportunity, or simply another brief candle about to flicker out. Each of these solutions becomes more plausible when you increase the number of habitable worlds. More habitable worlds mean more opportunities for filters to operate, more time for evolution to proceed along different time scales, more civilizations potentially hiding in the darkness. But there's a fourth implication that receives less attention. If red dwarf planets can be habitable, Earth-like worlds become dramatically less special. Our planet orbits a star that will exhaust its fuel and leave the main sequence in 5 billion years. TRAPPIST-1e orbits a star that will burn for 10 trillion years. From a long-term perspective, sun-like stars are flashes. Brief, energetic flares in cosmic history that burn bright and die young. The galaxy's future belongs to red dwarfs. They will outlive everything else. They will continue providing stable energy to their planets for timescales so vast that the current age of the universe is a rounding error. If life cares about longevity, red dwarf planets are superior habitats. Yes, the radiation is harsh. Yes, tidal locking creates extreme climates. Yes, photosynthesis struggles under infrared illumination. But these are engineering problems that evolution can solve given sufficient time. And time is the one resource red dwarf planets have in unlimited supply. This creates a disturbing anthropocentric bias in how we think about habitability. We defined habitable zones based on where Earth-like planets could maintain liquid water. We prioritized sun-like stars because that's what Earth orbits. We assumed that our specific stellar environment represented the template for life everywhere. But the galaxy doesn't care about our assumptions. The galaxy is 75% red dwarfs. If nature can solve the habitability challenges around red dwarfs, and TRAPPIST-1e suggests it might be possible, then the typical inhabited world in the Milky Way doesn't look like Earth. It looks like TRAPPIST-1e. Tidally locked. One hemisphere in eternal day under a dim red sun. The other hemisphere frozen in eternal night. Habitable ring between the two extremes where temperature allows liquid water and atmospheric circulation prevents collapse. Potential life adapted to near-infrared photons and high radiation fluxes, and climate zones that never change. This is the median inhabited world. Earth is the outlier. A planet orbiting an unusual star on an unusual orbit, with unusual axial tilt that creates seasons and day-night cycles and climate zones that shift over time. We evolved in anomalous conditions and then assumed those conditions were normal. The realization is humbling. For centuries, humans believed Earth was the center of the universe. Copernicus displaced us from the center of the solar system. Hubble displaced us from the center of the galaxy. Modern cosmology displaced us from any special cosmic location. We learned to accept that we occupy a typical position in an unremarkable region of an average galaxy. But we retained one last refuge of specialness. We assumed our planet was typical of habitable worlds. That Earth-like conditions were the standard template for life. That other inhabited planets would resemble ours in their basic properties. TRAPPIST-1e strips away that final refuge. If it has atmosphere and water and possibly life, it demonstrates that habitable worlds don't need to be Earth-like. They can be tidally locked hellscapes battered by flares under dim red suns and still maintain conditions suitable for chemistry and possibly biology. We're not just displaced from the physical center of the cosmos. We're displaced from the statistical center of habitability. We're the weird ones, the exceptions, the planets orbiting dying stars on temporary orbits under unstable conditions that won't last. The galaxy's future doesn't belong to worlds like Earth. It belongs to worlds like TRAPPIST-1e. Patient, resilient, bathed in radiation but protected by atmosphere, maintained through billions of years of volcanic outgassing and tidal heating. Hosting life, if life exists there, that evolved under fundamentally different conditions than anything we recognize. This shift in perspective affects how we search for biosignatures. We've been looking for oxygen and ozone because that's what Earth's atmosphere contains after photosynthetic organisms transformed it. But if most habitable worlds orbit red dwarfs, and if photosynthesis on red dwarf planets produces methane rather than oxygen because the organisms use different electron donors, then oxygen is not the universal biosignature we assumed it was. Methane might be more common, or hydrogen sulfide, or exotic organic hazes created by photochemistry we haven't considered because it doesn't happen in Earth's atmosphere. The diversity of potential biosignatures expands when you expand the diversity of habitable environments. Each stellar type, each orbital configuration, each atmospheric composition creates different chemistry and different potential signatures. The search becomes more complex, but also more interesting. TRAPPIST-1e represents one data point. One world where tentative atmospheric detection suggests habitability might be possible around a red dwarf. But the TRAPPIST-1 system contains 6 other Earth-sized planets. TRAPPIST-1, F, G, and H orbit farther from the star in or near the habitable zone. They receive less radiation. They might have better chances of maintaining atmospheres and water. Proxima Centauri b, orbiting the closest red dwarf to Earth at just 4.2 light-years, sits in its star's habitable zone. LHS 1140b and c, two planets orbiting a red dwarf 48 light-years away, are both potentially habitable. Dozens of similar systems are known. Hundreds more await discovery. Each one provides an opportunity to test whether TRAPPIST-1e represents an anomaly or a template. If 10 red dwarf habitable zone planets show no atmospheres, and TRAPPIST-1e is the only one with air, then E is special for reasons we don't understand. If 5 out of 10 show atmospheres, then atmosphere retention around red dwarfs is common, and habitability is widespread. We won't know until we observe them all. Webb's observing time is limited and competition is intense. But over the next decade, transmission spectroscopy of dozens of red dwarf planets will accumulate. Each observation adds information. Each detection or non-detection refines our understanding. By 2035, the statistical sample will be large enough to estimate what fraction of red dwarf habitable zone planets maintain atmospheres. That fraction determines how many habitable worlds exist in the galaxy. That number determines the likelihood that we're alone. If the fraction is 10%, 3 billion habitable worlds orbit red dwarfs in the Milky Way. Add a few billion around Sun-like stars, and the galaxy contains roughly 5 to 6 billion habitable planets. The odds favor life existing elsewhere. The Fermi paradox intensifies. If the fraction is 1%, 300 million habitable red dwarf worlds exist. Still a large number, but small enough that life might be rare. Intelligence rarer still. We might be alone in the galaxy by simple statistical bad luck. If the fraction is 0.1%, 30 million habitable worlds, the galaxy becomes lonelier, the filter becomes harsher. We approach scenarios where Earth-like intelligence occurs once per galaxy rather than millions of times. TRAPPIST-1e will help determine which scenario is real. Not alone, but as part of a growing dataset that constrains the prevalence of habitability around the galaxy's most common stars. The broader implication extends beyond biosignatures and life detection. It affects humanity's long-term future. If we survive the next several centuries and develop interstellar travel capability, where do we go? What stars do we target for exploration or colonization? Sun-like stars seem like obvious choices. Find a yellow dwarf with an Earth-like planet and establish a new home resembling the one we left. But Sun-like stars are rare and scattered. The distances between them are vast. Interstellar colonization targeting only Sun-like stars would be slow and sparse. Red dwarfs are everywhere. Within 10 light-years of Earth, there are 7 red dwarfs but 0 Sun-like stars. Within 20 light-years, there are 40 red dwarfs and maybe 5 Sun-like stars. The nearest potential habitable worlds almost certainly orbit red dwarfs, simply because red dwarfs dominate the local stellar neighborhood. If red dwarf planets can be habitable, they become the obvious targets for interstellar expansion. Close, common, long-lived. You could establish outposts around thousands of red dwarfs within a few hundred light-years of Earth, creating a network of settlements that would persist for trillions of years. But colonizing a tidally locked red dwarf planet requires adapting to conditions fundamentally different from Earth. Eternal day on one hemisphere, eternal night on the other. Radiation fluxes requiring protective technology or biological adaptation. Dim red illumination unsuitable for Earth plants and unsuitable for human eyes evolved for yellow sunlight. We would need to become something other than what we are, genetically modified to tolerate radiation and low light. Technologically augmented to function in hurricane-force winds and extreme temperature gradients. Culturally transformed by living on worlds where day never ends and night never breaks, and neighboring planets hang in the sky like additional moons. This is the far future that TRAPPIST-1e implies. A humanity spread across red dwarf systems throughout the galaxy. Adapted to eternal twilight. Living on timescales measured in trillions of years because the stars will never die. building civilizations that will outlast everything from our current era. Or, if we don't survive to reach that future, some other species will. Some civilization that emerges on a red dwarf planet or conquers the challenges of settling them. They will inherit the galaxy because they evolved in or adapted to the dominant stellar environment. Either way, the future is red. Red dwarf stars. Red dwarf planets. Life and civilization persisting under dim red suns while the rare, bright yellow stars burn themselves to exhaustion and fade to white dwarf corpses. We're living in the brief era when sun-like stars still shine, an epoch that will be forgotten in the deep future when red dwarfs host the galaxy's only remaining inhabited worlds. TRAPPIST-1e offers a glimpse of that future, a preview of what the typical inhabited world might look like when the current age of bright stars is ancient history. The empire of the red dwarfs stretches across 300 billion stars and spans trillions of years into the future. TRAPPIST-1e might be one of its earliest provinces. Or it might be sterile, and the empire remains unpopulated, waiting for life to eventually emerge, or intelligence to seed it. Either way, understanding TRAPPIST-1e means understanding the galaxy's dominant environment, the most common stellar type. The most likely habitat for whatever life exists or will exist in the eons to come. We're just starting to look. And already we're finding hints that our assumptions about where life can exist were too narrow, too biased by our own stellar neighborhood, too limited by what we see when we look up at a yellow sun from a planet that won't last. Light that left TRAPPIST-1e when you were born is arriving at Earth right now. Photons that filtered through whatever atmosphere might exist on that distant world, carrying spectral fingerprints of molecules floating in alien air, have been traveling through the void for exactly as long as you've been alive. If you're 20 years old, the light James Webb captured in 2023 began its journey in 2003. If you're 40, that light left TRAPPIST-1e in 1983. The photons don't care about your age. They travel at the only speed the universe allows, crossing the 40.66 light-year gulf between worlds at exactly 299,792 kilometers per second. Every second, new photons arrive. Every observation by Webb captures light that witnessed TRAPPIST-1e's surface 40 years in its past. We're not seeing the planet as it exists now. We're seeing it as it was when Ronald Reagan was president, or when the first Iraq War began, or when the Twin Towers still stood in Manhattan. This temporal displacement is fundamental to astronomy. It's also deeply unsettling when you consider what it means for searching for life. If biosignature gases exist in TRAPPIST-1e's atmosphere now, in December 2025, we won't detect them until 2065. If life emerges on the planet tomorrow, we won't know until 2066. The light speed delay creates an observational asymmetry that destroys any possibility of real-time interaction with whatever might exist out there. We can look, we can measure, we can infer the presence of atmosphere, or water, or methane, or complex organic molecules. But we cannot communicate, we cannot confirm, we cannot ask the planet's hypothetical inhabitants if they're actually there. This is the weight of distance. 40 light-years sounds close when you're discussing astronomy. Proxima Centauri is 4.2 light-years away. TRAPPIST-1 is only 10 times farther. 10 times 4.2. Nothing in cosmic terms. But translate that distance into human units and the weight becomes crushing. 40 light-years equals 378 trillion kilometers. If you could travel at the speed of the fastest spacecraft humans have ever built, Voyager 1 at 17 kilometers per second, the journey to TRAPPIST-1 would take approximately 700,000 years. Launch a probe tomorrow and it arrives in the year 720,026. Whatever civilization sends that probe will have long since vanished by the time it reaches its destination. Whatever descendants remain, if any survive at all, will have evolved into something unrecognizable from the species that built the spacecraft. Interstellar travel at sublight speeds is civilizational suicide. You must become something that persists for hundreds of thousands of years. Something that doesn't forget its mission across 30,000 generations. Something that maintains purpose and continuity while stars shift their positions in the sky and continental drift reshapes Earth's surface and ice ages come and go hundreds of times. We are not that thing. We can barely maintain continuity across centuries, let alone hundreds of millennia. Our longest-running institutions are a few thousand years old at most. The idea that we could build a probe, launch it toward TRAPPIST-1, and have anyone alive to receive data when it arrives is absurd. Even if we solve the engineering challenges of near light-speed travel, even if we build craft that travel at 10% light speed, the journey takes 400 years. 20 generations, long enough that everyone who remembers why the mission launched is dead. Long enough that languages change and cultures transform, and the species that arrives at TRAPPIST-1 is related to but distinct from the species that departed Earth. This is the tyranny of the light speed limit. It doesn't just prevent faster-than-light travel, it makes interstellar exploration on human timescales functionally impossible. We can send robots, we can send frozen embryos to be gestated by machines upon arrival. We can send digital minds uploaded into computers to be instantiated in synthetic bodies at the destination. But we cannot send ourselves, not as we currently exist, not as biological organisms with lifespans measured in decades rather than centuries. The distance is too vast, and the speed of light is too slow, and human flesh is too fragile. So we observe. We point telescopes at worlds we will never visit, and we measure the chemistry of atmospheres we will never breathe, and we search for life we will never meet. This is the limit of what's possible, given the physical constraints of the universe we inhabit. Unless we're wrong about those constraints. Unless physics we don't yet understand permits faster-than-light travel or wormholes or folding space or quantum tunneling of macroscopic objects across interstellar distances. The mathematics of general relativity allows such possibilities under extremely exotic conditions involving negative mass or infinite energy or rotating black holes. But exotic solutions to equations are not engineering designs. You cannot build a warp drive from a mathematical construct that requires negative mass when negative mass doesn't exist. You cannot create a traversable wormhole when the energy requirements exceed the total mass energy of the observable universe. Waiting for physics to rescue us from the light speed limit is hoping for magic. It might happen. Unlikely things sometimes occur. But planning based on unlikely physics is delusional. We must operate within the constraints that appear to govern the universe as we currently understand it. Those constraints mean that TRAPPIST-1e remains forever distant, 40 light-years away, observable, but unreachable. We detect its atmosphere from telescopes in orbit around Earth or sitting on mountaintops in Chile or Hawaii. We measure its chemistry and search for biosignatures and wonder if anything lives there, but we cannot go there, not in any time frame that matters to individual human lives. This creates a strange relationship with the discovery. If Webb confirms that TRAPPIST-1e has atmosphere and water and methane and possibly biosignatures, we will know that a potentially inhabited world exists 40 light-years from Earth. We will have answered the question, are we alone, with a tentative no. But nothing changes for us personally. The inhabited world is too far away to visit, too far away to communicate with given the 80-year round-trip light travel time. Too far away to affect human civilization in any practical sense. It exists, it's inhabited, so what? The so what is philosophical rather than practical. The knowledge that life exists elsewhere, even if that life is microbial mats producing methane on a tidally locked world we'll never see, transforms our understanding of our place in the universe. We are not alone. We are not unique. The chemistry that produced us also produced something on a world orbiting a dim red star 40 light-years away. Life is not a singular miracle that happened once in the observable universe. It's a process, a chemistry that emerges when conditions permit. A phenomenon that occurs repeatedly across billions of planets. This changes meaning. If life is common, then Earth's biosphere is just one instance among millions or billions. We're not precious guardians of the only life in the cosmos. We're examples of a general phenomenon that happens wherever conditions allow. Some people find this comforting. We're part of something larger than ourselves. The universe is filled with chemistry similar to ours. Life and perhaps intelligence emerge naturally from physics operating over billions of years. Others find it horrifying. We're not special, we're generic. Our existence carries no cosmic significance beyond the local significance we assign to it ourselves. The universe doesn't care about us because the universe is full of things like us scattered across billions of light years. Either reaction is valid. The universe doesn't have opinions about how you interpret evidence of life elsewhere. It simply is. Life either exists on TRAPPIST-1e or it doesn't. Our emotional response to that fact doesn't change the fact itself, but it changes us. Knowing that life exists on another world, even tentatively, even with statistical confidence below 5 sigma, even pending confirmation from observations that haven't happened yet, shifts perspective. You look up at the night sky and you know that some of those stars have planets and some of those planets have atmospheres. And some of those atmospheres might contain the chemistry of life. The sky stops being empty, it becomes populated. Not with visible civilizations or detectable megastructures or radio signals from alien societies, but with the potential for life. The possibility that evolution operated elsewhere, that metabolism happens on distant worlds. That chemistry organized itself into self-replicating patterns that harvest energy and reproduce and adapt across billions of years. TRAPPIST-1e might be the world that proves this. Or it might be sterile and some other world provides the proof. Proxima Centauri b, LHS 1140c. One of the thousands of potentially habitable exoplanets we'll discover in the coming decades as telescope technology improves and survey completeness increases. Eventually, one of these worlds will show biosignatures we cannot explain through abiotic processes, oxygen plus methane in disequilibrium ratios, dimethyl sulfide at concentrations requiring biological production, vegetation red edges indicating photosynthetic surface cover. The evidence will accumulate until the probability of life exceeds 5 sigma and the discovery becomes official. We will have found life beyond Earth. Not intelligent life necessarily, not technological life that builds radio transmitters and sends messages across the void. Just life, chemistry that reproduces, biology that exists. And we will still be 40 light-years away from it, separated by distances we cannot cross and timescales we cannot survive, looking at something we can measure but never touch. This is the nature of cosmic discovery in the 21st century. We have the technology to detect the chemistry of worlds circling other stars. We lack the technology to reach those worlds. We can see farther than we can travel. Our vision exceeds our grasp by factors of millions. Perhaps this will always be true. Perhaps the light speed limit and the vast distances between stars mean that each intelligent species remains isolated on its homeworld, looking out at a universe populated with other isolated species, all of them observing each other, but none of them making contact. The galaxy becomes a collection of lonely islands, each one inhabited, each one aware that the other islands exist. None of them able to bridge the distances between. Civilizations rise and fall in isolation, evolving their own philosophies and technologies and cultures without influence from elsewhere. Or perhaps we'll develop technologies we can't currently imagine. Perhaps the physics we don't understand permits travel at speeds that make interstellar distance negotiable. Perhaps we'll upload our minds into machines that can survive million-year journeys through space. Perhaps we'll become something that isn't bound by biological limitations, and therefore isn't trapped by timescales measured in decades. But until that happens, if it ever happens, we remain limited to observation. We point our telescopes at TRAPPIST-1e, and we measure photons that traveled 40 years to reach us, and we infer the existence of molecules in an atmosphere around a planet we will never visit. The weight of those 40 light-years presses down on every conclusion we draw. The distance is unbridgeable with current technology. The planet exists in our observable universe, but outside our reachable universe. We can know it exists without ever being able to go there. This is simultaneously the triumph and the tragedy of modern astronomy. We've developed the capability to detect and characterize worlds orbiting other stars. We've learned that planets are common, and habitable zones are numerous, and potentially habitable worlds number in the billions. We've brought the universe into focus in ways that would have seemed impossible 50 years ago. But we've also learned that the universe is larger than we can ever explore. that most of what exists lies beyond our reach, that the light speed limit enforces cosmic isolation on scales we cannot overcome through engineering or determination or patience. TRAPPIST-1e represents this duality, a world we can study in detail, measuring its size and mass and orbital parameters and atmospheric composition, but also a world we cannot reach, cannot sample, cannot confirm through direct investigation. We know it through spectroscopy and statistical inference and computer modeling. We cannot know it through direct experience. The planet exists in superposition, simultaneously real and abstract, observable yet untouchable. A place with chemistry and possibly biology and potentially oceans and atmosphere, but also just a set of numbers in a database. A spectrum on a graph. A probability distribution describing molecular abundances. 40 light-years is close enough to detect, far enough to remain forever alien. This is the distance that defines early 21st century astronomy, close enough to observe, too far to reach. We stand at the boundary between ignorance and knowledge, capable of seeing but not touching, capable of measuring but not visiting. And we will stay at this boundary for the foreseeable future. The technology to reach TRAPPIST-1e doesn't exist. The physics that would permit faster-than-light travel remains theoretical at best. We have no realistic plan for crossing 40 light-years in human lifetimes. So we observe. We wait for more data from dual transit observations in 2026. We plan for future telescopes with better sensitivity and higher spectral resolution. We search for biosignatures and transmission spectra and prepare for the possibility that life exists on a world we measured but never met. This is the weight of 40 light-years. Heavy enough to prevent contact, light enough to permit observation. The perfect distance for tantalizing discovery without resolution. Close enough to know something is there. Far enough that we'll never be sure what that something is. The spectrum doesn't lie, but it whispers. 0.3% methane at 3 sigma significance. Nitrogen atmosphere tentatively preferred over bare rock. Surface conditions possibly allowing liquid water in a habitable ring between eternal day and eternal night. A world that should be dead but might be alive, orbiting a star that should have sterilized it but maybe didn't. This is what 40.6 light-years of void delivers to James Webb's detectors. Ambiguous data. Tentative conclusions. Probable rather than certain. The most sophisticated observatory ever built pointed at one of the best potentially habitable worlds we've found, and the answer it provides is maybe. Maybe atmosphere exists. Maybe water pools on the surface. Maybe life produces the methane. Maybe we're looking at the first confirmed inhabited world beyond Earth. Maybe we're looking at bare rock and statistical noise. The observations scheduled for 2026 will narrow the probabilities. They won't eliminate the maybe. You're receiving this information 40 years after it left its source. By the time you hear these words, new photons have arrived from TRAPPIST-1e, carrying information about the planet's current state. Information that won't be decoded for years because telescope time is limited, and analysis takes months, and confirmation requires multiple independent observations. We're always looking at the past, always waiting for light that's already traveling toward us. Always trying to reconstruct reality from photons that witnessed events decades ago. This is the only way to do astronomy across interstellar distances. Wait for light, measure what it tells you, infer what existed 40 years ago at the location the light originated. Hope the planet hasn't changed too dramatically in the intervening time. TRAPPIST-1e is teaching us what we are, a species capable of detecting atmospheric chemistry on worlds we cannot reach. Sophisticated enough to search for biosignatures across 40 light-years, advanced enough to wonder if we're alone, but limited by physics we didn't choose and distances we cannot overcome. The red dwarf graveyard might contain survivors. The impossible might be real. Life might exist in radiation environments we thought were lethal. Biology might adapt to eternal twilight under dying suns. The galaxy might be filled with inhabited worlds we've been ignoring because we assumed our stellar neighborhood was typical. We assumed wrong. The universe doesn't care what we assume, it operates according to physics. Chemistry follows rules. Life emerges or doesn't based on conditions that exist, not conditions we prefer. If you enjoyed discovering what hides 40 light-years from Earth, if this journey through transmission spectra and stellar violence and the weight of cosmic distance delivered the existential perspective you needed today, hit that like button. Subscribe for more revelations about worlds we can measure but never meet. Share this with someone who still believes Earth is special. The dual transit observations continue. The data accumulates. The statistical significance inches higher. Within a year, we'll know if TRAPPIST-1e's atmosphere is real or a statistical artifact. Within a decade, we'll know if the methane requires biological explanation. And we'll still be 40 light-years away, staring at a world we discovered but cannot visit, wondering if something there is staring back across the same unbridgeable void. The universe is larger than we can explore. Life might be common. Intelligence might be rare. Distance makes everything unreachable. But observation makes everything visible. This is the age we inhabit. Eyes capable of seeing across light years. Bodies trapped by physics and limited by time. We look outward, and we find hints of worlds like ours and worlds nothing like ours, and all of them exist beyond the boundary we cannot cross. TRAPPIST-1e changes everything about where life can survive in this galaxy. But it changes nothing about our isolation in the cosmos. We remain alone in the only sense that matters. Alone with our thoughts about distant worlds. Alone with data that might indicate life. Alone on a planet orbiting a star that will die while the red dwarfs burn for trillions of years. The discovery is real. The distance is permanent. The wait for confirmation continues. And somewhere 40 light-years away, photons are leaving TRAPPIST-1e right now, carrying information we won't receive until the year 2065, when everyone reading these words will either be middle-aged or dead, or transformed into something we can't currently imagine. Light travels. We measure. The universe remains vast. Life might be everywhere. And we're still here, staring up at dots of light in the darkness, wondering what they mean.